Hello, good afternoon, everyone. We are going to shortly start our session. So, I'd like to know from someone if I'm audible or not. You can text in the message box. Okay, fine. It seems I'm audible. Once again, thank you everyone for connecting to us from various corner of the world. We have participants from total around 10 countries, and I am very much excited to see uh, this much of participation in our session. And for that, thank you to everyone. So, without wasting time, let us start our session. Okay, so you already know I am Tajul Islam, currently pursuing my PhD at IIT Roorkee in the Department of Earthquake Engineering, and I am particularly working in the performance-based seismic design of buildings subjected to corrosion of rebars. Okay, so basically, as part of my PhD, I have worked for last 3 years on performance-based design. So whatever skill I have gained in this journey of 3 to 4 years, that I'll try to share with all of you. What I feel, it's not like I'm expert in this area, that's why I'm doing this one. So my intention is whatever I have learned, and I want to share this with the people who are interested in this topic. And also, we are doing some like consultancy work also in our department. We get the design from different industries, different consultancy, and we get to do the proof checking of all those. So while doing those kind of work, interacting with the people from industry, we understand there is a lot of misconception about the structural design. And based on that, we have tried to resolve the issues what we get from clients, and we have done some like experimentation on the modeling. And in that process, whatever we have learned, I'll try to share all those things. Okay. So to start with, I'd like to share this meaningful caption. In fact, it's a reality if you see the past experience with the earthquake, wherever it has occurred. You can take recent example of earthquake in Turkey and most recently earthquake in Japan. And the consequences of both of these earthquake are completely different and eye-catching, you can say. If we talk about earthquake in Turkey, it was highly destructive. Lot of people lost their lives, then property. Lot of buildings, high-rise buildings collapsed. But on the other hand, if you see the earthquake in Japan, which was also destructive in terms of the intensity compared to the Turkey earthquake, although it was also damaging, but compared to the damage occurred in the Turkey earthquake, the earthquake in Japan was very much minimal, you can say, although around 40-50 people lost their lives. But overall damages compared to the Turkey earthquake was very much negligible, you can say. Now, you can think how and why this have occurred. This difference has happened. Although both the earthquakes were different, both the earthquakes were similar in terms of the intensity of ground shaking. So that's why this earthquake don't kill, but the faulty design does. That comes into question. When you do not design the structure properly, whoever is responsible for the design. So definitely it is going to affect not only 1 or 2%, entire society. Okay. So we as a structural engineer should be responsible and should take this responsibility to means rectify this error, whatever is going on currently. Okay. So here we start with the performance based design. And the very first thing what you have to do is to consider the expected properties of material, whatever you are going to use in your design. Normally in RC building, if we talk about, we use two kind of material mostly. There can be other materials also, but mostly we use concrete and steel. So whenever you design, you use the nominal properties based on the specification given in your respective code, depending on which country you are. Uh, as an example, here what I am showing is with respect to our Indian code. Okay. So in Indian code, FCK is defined as the characteristic strength, this one. And this characteristic strength is defined as the strength which is corresponding to 95% confidence line. Means in the 95% of cases, the strength of that
Excuse
material.
me, sir.
Yes.
Sir, I think your slide is not moving.
Slide is not moving.
Okay. 1 minute. Let me check once again. Is it the first slide only?
Yes, sir.
Second one. Now it is start.
Okay. Can you see that concrete, steel, and one probability distribution?
Uh,
It is
I
estimation of
think
structure.
slide fourth.
I
This is
think
the
there
third
is.
slide.
Yeah, currently I am in the third slide.
Yes.
Okay, then it's fine. I am discussing in the third slide only. Okay, yeah, thank you. Wherever this kind of problem occurs, please let me know. Thank you. So I was talking about the concrete, the characteristic strength defined in Indian code FCK, which is corresponding to 95% confidence line. That means in the 95% cases, the strength of that material will be higher than the specified value. For example, if I talk about M20 concrete, which is defined as per again Indian standard, means the strength of concrete is defined as the 20 Newton per mm square or megapascal, you can say. So the 95% confidence line shows that in the 95% of cases, for example, if you take 100 sample, out of those 100, 95 samples will have strength higher than 20 MPa. This is the meaning of characteristic strength. And this is the median value defined, FC median. Okay. Now, with respect to the characteristic strength, means along with the characteristic strength, if you add 1.64 into sigma of concrete, okay, this 1.64 is the difference between, means deviation between the median and the 95% line. This is the property of standard probability distribution actually, and I am talking about the normal distribution. So this 1.64 will come from that distribution. Now this sigma c, this is again the standard deviation based on the number of samples taken for the experimentation. Okay, a large number of sample. So from that distribution, you get in case of concrete, it is near to 5 MPa or so. Okay, so this value you can use here. Now this FCK definition can be different with respect to different codes. If you are from some other country, maybe this FCK definition can be some other thing. Instead of 95%, they may define in some other confidence line as well. Okay, so you take care of this one with respect to your country code. Okay, but what I want to emphasize here is that you have to use the most expected value of the strength for your structure. Now, according to this Indian standard definition, our expected strength will be this one, zero point 0.8 into 0.85 into plus this median value. If you take this FCK plus 1.64 into sigma, you are going to get this one, FC median. Okay. Now with that, why we are multiplying these two factor, zero point 0.8 into 0.85. Okay. Actually, in the structure, you have to use the strength in terms of the cylinder strength. Okay. But most of the times, in our Indian scenario, we do the concrete testing using concrete cubes. So there is a provision that when you use the concrete cubes for your testing, and to convert this into cylinder strength, you have to multiply by the factor of zero point 0.8. Okay. Then again, you have to multiply with the factor 0.85. This is because of the size effect. Actually, when we do the testing, the cube size is very small, 150 mm by 150 mm by 150 mm cube. But our structure is very much larger compared to that size. So to take into the effect of this size difference, we multiply according to the clause code provision. We multiply this factor 0.85 again. So overall, you are getting this as the expected material strength for the concrete. Okay. Now here only this term FCK you have to take care of with respect to your country code. Okay. Similarly, again you have the expected strength for steel. Fy is the defined value as per code. For example, if I say Fe 500, which is 500 MPa or 500 Newton per mm square grade, with that again you have to add 1.64 into sigma, similar standard deviation value. But here you are not getting this one because in case of steel, whether you take small size of specimen or large size of specimen, strength will be same in all the cases. Okay, so these factors are not going to come here. Then similarly, in case of ultimate strength also you have similar expression. Okay. So like this, you have to use this expression to determine the expected material properties. And this is the very first thing you have to do in case of performance-based design. When you start the performance-based design, this should be your first step. Okay. Now, some people have asked me before this session, what is actually the performance-based design? So I'll just briefly say about what is the background in the performance-based design. When you design the building as per your code, you like here the nominal properties you consider, and there are some direct approach given for the design of structure based on some decision taken by experts in the code committee. So you design the building to be on the safer side, but you actually do not know how much safety margin you have kept in your design. Okay. To check that how much actual strength of the structure, there should be some procedure. So this is one of the procedure recently developed and currently becoming popular among the people in industry also. In this performance based design, we determine the actual capacity of the building in terms of strength as well as displacement. So you will get to know. First, you will design the building using your code, whatever code you are using the same code. You will first design the building. Then you will apply the performance based design on that building, what is already designed using code, to determine the actual capacity and actual displacement. Means capacity in terms of displacement and force. Actual capacity and displacement you will be determining using this concept. Okay, so this is performance based design, and we'll see when we go further with different steps, we'll see what we are actually doing. But overall, this is the scenario what you do in performance based design. Okay. I think I'm not able to change my slide. Okay. Sorry. Okay, so the next part of discussion, we have to talk about the confinement. So as an example, I have taken these two scenario of concrete construction. For example, let's say this is one column, RCC column, and this is another RCC column with different arrangement of lateral reinforcement or stirrups or lateral ties, whatever you say. Now, see, in the first case, what happens? Only rectangular stirrups, two-legged, in both X and Y direction. Two-legged stirrups are given, and in another case this is two legged and one diagonal also. Okay, so you can say this is four legs or something like that. Okay, now based on this interpretation, if you see in the first case, the concrete outside the cover and some portion inside the cover as well, which is already spalled off, means removed because of damage. Okay, when this column is subjected to some loading, maybe for example, let's say earthquake loading or some kind of loading, then the portion which is not protected will be removed or will be spalled off. Okay, now the portion or quantity of concrete which is going to be falling off depends on how much protection you have provided. That protection is going to be in terms of lateral reinforcement. Okay. So in the first case, there was some protection in terms of this lateral tie where two legs are provided. But in the second case, the protection amount is higher compared to the first case. So the concrete quantity of concrete which was protected is also higher in the second case. Similarly, if you increase the protection again further, then your quantity of concrete which is going to be protected will also increase. Okay, so this is the meaning of confinement, how much you are protecting or how much you are confining your core concrete with some kind of lateral reinforcement. Okay, now this protection also depends on the arrangement of your lateral reinforcement. In the figures here below this, three different scenarios are given. If you can see, if your reinforcement lateral reinforcement arrangement is like this, then the portion which is highlighted here will be protected and the uh, unshaded portion will be removed or will be spalled off during the loading or earthquake loading, you can say. Okay, then if you take the second example, cross section B, here the reinforcement arrangement was similar, but number of lateral ties increased. So consequently, your the protection protected concrete quantity is also increased. Okay, so based on this, you can say the arrangement of lateral ties also affects your confining quantity of concrete. Okay, so you have to take care of that when you are designing the structure and giving the lateral reinforcement. What arrangement you are actually following, that is also important. And what happens, suppose this hook portion, normally codes suggest you have to provide 135-degree hook, but in field actually, when this casting is going on, people mostly try to ignore this one because it creates difficulties in placing your lateral ties. Okay, but based on that ignorance, what happens? Structure loss means it loses most of the strength or capacity what it's supposed to have. Okay, so just a small thing to do here. Maybe it takes some extra time or some extra work you have to do. But if you don't do that one, it will be highly destructive during the event of earthquakes. So you should not ignore all these things, minor things. Okay. Similarly, if you see along the length or along the axis of the member also, this was in the cross section, how much quantity of concrete is protected. So if you see along the vertical direction also, here you see how it is protected because of the lateral reinforcement. So what happens? Now, in terms of plot, if we talk about, like, all of you may be knowing what is the stress strain curve of concrete. Okay, in graduation also you study stress strain curve of concrete. So if I take the first curve, this one, this is the example of stress strain curve of unconfined, means normal concrete, you can say plain concrete. For example, you are testing a concrete cube of 150 by 150 by 150. Okay, so without taking anything in consideration, if you test that concrete, then you expect this strength. Okay, and in horizontal axis you see the strain, whatever strain you normally measure, that one longitudinal strain, and it is very much negligible compared to these other curves. This I'll talk about now, but just compare this difference in the strain values. These curves are having the strain limit up to 0.05, but this one plain concrete is having less than 0.01 or maybe 0.005. So it is almost one tenth. So you can say, compared to the unconfined concrete, your confined concrete can have the strain limit up to 10 times of this normal concrete. If you talk about in terms of strength, that difference is not very much, but still it is higher. Okay. Here you have around 4000 Pascal per PSI, means Pascal per square inches, 4200 or so. And in case of confined, it is around 6000. But when you design the building for earthquake loading, compared to your load capacity, displacement capacity matters most. Okay, so that's why you do not go by this one. Our confined concrete is not giving means higher strength. It is marginal, that difference. Do not go by this impression, because ultimately your displacement capacity is going to take the major role during seismic event. Okay, and here you see considerable difference. Now see these three curves, uh, this based on these three different arrangement of your confining bars or lateral ties, you can say. So in this case, which is represented by alphabet A, here you see this is giving the strength as well as strain higher compared to all others. Now, if you take this arrangement of lateral ties, which is two-legged, you have the means strain capacity is almost similar in all the cases, but strength capacity is less compared to other two arrangement. So these things you should keep in mind. The arrangement of lateral ties also plays a very important role. Next, when you do your nonlinear design, nonlinear analysis, you have to use the nonlinear properties of your member like beams, columns, etc. That nonlinear properties in terms of capacity, moment capacity, and your rotation capacity. Okay. We normally follow ASC code or American code. Recently, SCI 369 code also came, that also gives the nonlinear specification, modeling parameters required for nonlinear modeling. These things are given in the code. But if you want to understand how actually those values came, or you want to define your own backbone curve, instead of going for a code, you want to define your own values of those parameters. How to determine those? So this is one approach. You can determine moment curvature of your section. For example, you have a column section of 400 by 400 mm, and for example, 2% of reinforcement you have provided, and you want to determine the capacity curve for that column. How can you do that? So this approach you can follow. Here I have used this Mender's confined concrete model, uh, basically to determine the confined concrete strength stress strain curve, what I have just shown in the previous slide. You can determine that curve, and using that curve parameters and based on the section analysis, you can determine the moment capacity. Okay. Now, when you try with this method, first thing you have to calculate is this one, the peak strength of your confined concrete. Okay, FCC. This is similar to the peak strength of your normal concrete. In stress strain curve, you have one peak strength at corresponding to 0.00 strain. Okay, so this axis is similar to that one, but for confined concrete. Okay, so expression is going to be this one. FCC is equal to FC into 2.54 into square root of this FL divided by FC. FL is again expressed here, and FC already I told this is the normal concrete strength, means unconfined concrete strength. Okay, so using this expression you determine FCC, then corresponding strain, at what strain this strength was, that strain you have to calculate. So this is to be done using this expression epsilon cc. Okay, so again epsilon cc is equal to some parameters then multiplied by, it is also a function of fcc divided by fc. So you again use this expression to calculate epsilon cc, and epsilon cu, this is the ultimate strain. It means if you see the previous slide, this ultimate strain. Okay, so this will be calculated using this expression. This is again function of one parameter rho v, then multiplied by fy by fcc into epsilon su. So this rho v is called the ratio of confining reinforcement provided in your section. Okay, so this is expressed here in this expression. Rho v is equal to asx divided by d into s plus asy divided by b into s. So d and b are going to be your section dimension, means gross dimension, and s is the spacing of lateral ties. Okay, then this fy is the nominal strength of your steel, means expected, not nominal. Sorry, here everything is going to be expected, nothing nominal should be used. Okay, so fy is the expected yield strength of your steel, then divided by fcc multiplied by epsilon su. This epsilon su is the maximum strain of your steel, means again if you take the stress strain curve of steel, the ultimate strain of that steel is going to be epsilon su. Okay, so some of you might have been already knowing that in case of steel, as per our Indian standard, we use the steel which is having more than 14.5% of strain. Okay, so you can take 14.5% as epsilon su in this case. But again, when you consider this for earthquake loading, it should be limited to 0.05. Okay, not 14.5. So you can use this expression to determine these parameters. Then once you get these parameters, then your means basically your stress strain curve for confined concrete is defined. Okay. Then after defining the confined concrete, you are going to determine the moment capacity for the section, that I'll talk in the next slide. But before that, here you see when you determine this FL, which is basically confining pressure, means this reinforcement, whatever lateral ties you have provided, how much pressure it is providing to the core section. Means when protecting the core concrete, it will be providing some resistance pressure, right, to the concrete. So how much actually that resistance pressure, that will be calculated using this FL. Okay, so this is again function of one parameter sf, which which is the shape factor basically. It means it depends on the shape of your cross section, whether it is a square section or is it a rectangular section or is it a circular section. Okay, you can imagine it like that. When the section is circular, it is most effective in protecting the central or core concrete, because it is the optimum shape. Any shape, ultimately if you stress it, it will try to become a circular shape. For example, you take a rectangular shape and you stress it from all the directions outward. So what will happen, it will try to become a a circular shape. Similarly, you take some other shape, square shape or elliptical shape, whatever shape you take, ultimately it will try to become a circular shape. So finally, circular shape is the most effective one in protecting the concrete. That's why this factor, depending on the shape, is given as 1 for circular, which is most effective, then 0.75 for rectangular, and zero point 0.5 for square section. Okay. Next, see, this already you have studied in your graduation. Maybe you have forgotten, but I'll try to brush it up again, no problem. So you can determine the capacity of any section manually using the section analysis concept. What you need is you need the strain distribution. and you need the stress distribution for the materials you used. This distribution of stress is shown for the concrete, but for steel I have not shown. You can understand this one. Stress strain curve for steel is also there. Okay. Now you have any section, you will have some neutral axis where there is no strain, there is no stress. Okay. And above the neutral axis, you say that is compression zone, and below the neutral axis, you say that is tension zone. Okay. And code says that the concrete portion in the tension zone should be. Sorry for the interruption. Actually, recording was stopped, so I had to restart this one. So I think I am audible. If not, please let me know. So
Yes,
we
sir,
are
you are audible.
okay. Thank you. So we are discussing the section analysis. The portion above the neutral axis is called as the compression zone, and below the neutral axis will be called as the tension zone. And the extreme strain on the tension zone, which is at the level of steel, is epsilon st, and extreme top level stream. uh, At the extreme fiber in the compression zone will be the strain for concrete. Okay. Similarly, at this level, you will have some strain for steel also, but the distribution will be similar. This same distribution you can use for concrete as well as strain because of the strain compatibility effect. It means the concrete and strain will be deformed similar in the same at the same point of time and together. Okay, so there will be strain compatibility all the time. We assume that although that will not be there all the time during earthquake, when cracking occurs it fails, but we assume there is the strain compatibility, so same strain will be followed for steel as well as for concrete. Okay, now see, for this compression zone, the resultant force you can represent by this Cc, and this resultant force will be acting at some centroid point of that force, maybe at a distance of, you can say, a from the top or x1 from the top, some interpretation you can give. Then you also have some compression force because of this steel, which is again in the compression zone. Okay, so this you can say Ct. Similarly, you have the force due to the steel at the bottom, which is under tension, and this you can represent by T. Okay, and if it is column, you also have the axial force, which is again compression by nature, means mostly there can be tension axial force also, but that time it will be negative P, you can say minus P. But here I am taking P as compression. Okay, so you analyze this section for this condition. Sorry, for this condition, C is equal to T minus P, means this is coming from the equilibrium condition. Your total force, summation of total force should be zero. So from that equilibrium condition is coming. Total compression force should be equal to the resultant tension force. So resultant tension force means this tension force minus this compression force, or you can say this P force, you can bring it to this side, so it will become C plus P, again total compression force. So you determine this force and try to satisfy this condition. Okay, once this condition is satisfied, at that point you have to note down the neutral axis. Okay, so after that you determine the moment capacity about the centroidal axis. In case of column, if your axial force is present, you have to take the moment capacity about the centroidal axis, means about this axis. Okay, so it will become Cc into this lever arm, then Ct into this lever arm, plus T into this lever arm. So that will be your moment capacity. Okay, so you get your neutral axis, you get your moment capacity, and next thing is you have to determine your curvature. Okay, so the curvature is going to be simply this strain divided by this neutral axis. Okay, So at each strain level, you can determine this one. So whatever process I have just explained, this should be done at different strain levels. So this I have just explained for a single strain point. For example, epsilon st is equal to 0.001. Okay, and if you're taking this, let's say 0.001 only, I am taking this one, and I am trying to satisfy this condition. Okay, so once this condition is satisfied and I calculate the moment capacity, then I have noted at this strain level, this is the moment and this is the curvature. Then go to next strain point, epsilon is equal to 0.005, for example. Then you follow the same procedure. Then next strain point, again follow the same procedure, and this should be done for the entire range of your stress strain curve. Okay, once it is done, then you can plot moment versus curvature in XY axis. Okay, so this is the overall concept of your moment curvature analysis. Now, this concept, whatever I have just explained, this concept is applied in the software. For example, ETAPS, SAP. Then I have also means told you about STKO, which we'll be using. So all the design analysis software implement this moment curvature based on this concept only. They do the section analysis, maybe some numerical algorithm to make it faster. Okay, but the background concept is this one only. Okay, so what we'll do at this stage is, right, so far we have explained this one, and we'll try to see using different softwares now. Okay, how it is actually done in the software and how we can do it manually. Okay, so before going to that demonstration, I would like to show this one. Okay, here you can see I have determined using this orange line shows the moment curvature using ETAPS. Then this gray color shows that determined using STKO, and this blue color shows using SAP 2000, and this yellow line, this one, using the manual calculation. Manual calculation in the sense I have implemented this one. For confined concrete, I have used Mender's model. Then I have used this section analysis, and I have implemented it in a Python code. Okay, so using that code, I can determine moment capacity for different means whatever section you give, it will give you the moment curvature. Now, this difference in strength, again, it depends on what actually you have done with the code. Okay, whatever parameters you are defining, according to that, your code will give you the result. Okay, I have never compared with the other software. Maybe I have missed some parameters, so it is giving this difference. I have to look at it, but you can make it. I just want to say that. Okay. Now we'll go one by one. First, we'll start with SEP 2000. Then we'll start with ETAB. After that, STQ, and finally we'll see the Python code for that. Okay. Okay, so at this point, I have to let you know this one. Whoever is first time user of SAP or ETAPS, don't worry. When we start with our actual building model, again, all the steps, whatever you need for defining materials, defining section, everything you'll come to know. We'll do step by step. Okay. So at this point, don't worry. But still, I'll show whatever steps we have done, but briefly without explaining in details. Okay. So first, what we do is we define the material. Here I have defined FE 500 according to our Indian standard. Okay. So what inside you can say here? This is the nominal yield strength. This is the nominal ultimate strength. Means this is the strength which is defined. Okay. For example, FE 500. So this is 500, and this is the expected one. Okay. So I have shown you expected strength is equal to nominal strength plus 1.64 into sigma. Okay, so if you use this one, you'll get this expected yield strength. Similarly, if you use that concept to the ultimate strength, you'll get this one. Okay, now here you need the sigma value for determining that. let's say expected ultimate strength is equal to nominal ultimate strength plus 1.64 into sigma s. So that sigma s is normally between 30 to 50 in case of steel, and 5 already I told in case of concrete. Okay, but here this you will get using 30, not 50. Okay, so normally we have done some calibration also, and we found 30 is appropriate when you use for the expected strength based on some experimental results. Okay, so you can use 30 MPa for sigma in case of steel. Okay. Then other parameters needed for normally when you do the analysis for buildings, some nonlinear parameters also. This will not talk about now. Okay, when you started the building, that time we'll discuss again. Similarly, I have defined for transverse steel FE415 and the concrete grade M30. Okay, so again here you see, as we are dealing with the expected properties, this property, whatever is written here, expected concrete compressive strength, it should be expected. Okay. Normally it is defined as 30 MPa nominal strength, but this should be taken as expected. So how you get, if you have calculator, you can calculate. It was 0.8 into 0.85 into FCK, which is 30 plus 1.64 into 5. If you do that, you're getting 25.976. Okay, so this is how you have to determine the expected material properties. Then after doing this, you go to your section properties, frame section, and add new property. Here you have some by default section shapes and materials, but you have to go to section designer for determining the moment capacity. Okay, so here you get it. You click on this drop down, then go to other section and section designer. Okay, and the base material you have to choose is M30, which is concrete. Then go to concrete column, and it doesn't matter whatever option you choose here, it doesn't matter. Okay, at the moment, then click on this and you create a section. Here different icons are given for different purpose. Now I'll select this rectangular one and just click anywhere. Okay, so it has given some default section. I have to check now which section is there. This is 400 by 500 by 500. I have already created the section, so I will not change anything. I'll just show how you have to do, and I'll use the section which is already defined. Okay, so here you define your section, and material is already defined here, and reinforcing you have to click as yes, and it is asking confinement, what kind of confinement you have provided. So you have to click on Mender's confined, and it will show you this bar. Okay, this tab. So confinement material is asking here. We have defined Fe415 for confined concrete, means transverse steel, and the diameter of transverse steel. So if you go by the Indian standard, 10 diameter, let's say we are using. Okay, then the spacing of transverse rebar, let's say 150, then 3 legs. And you can also see how these properties are changing when you modify these parameters. Okay, as you increase the number of legs, your strength is increasing, and along with the decreasing of the spacing also, this is increasing. Okay, so like you can imagine how these parameters affects your confined proportion of the concrete. Okay, so like this you have to do, then click OK. Now see, it is showing some default arrangement of reinforcement also. So you may have different number of rebars and different diameter. So what you have to do, you just click on any of the diameter, then right click. Okay, and here you see the bar diameter. Again, as per Indian standard, let's say I want to use 25 diameter for corner bars, and remaining thing automatically it will calculate. Okay, and also if you want the same properties for all the corners, you can click on that. Sorry, all the edges, you can click on that. Okay, then sorry, I think I didn't click that. So you can do this. Then for corner also, and apply to all corners. Then you can do this. Okay, so this is the thing you have to do in the section designer. Now this is the default section shape which is available in the software. Okay, but suppose you want to do some customized shape, you can do that by using some lines. That option I will not discuss here. You can explore. This is the interface you have. You can explore what different option does. Okay, you can do that also for customized section for different type of shapes. Okay, after creating the section, then you click on this one to get your moment curvature, and here you see this is the moment curvature plot for zero axial force. Here you have to define the axial force, how much you have, and it is written tension is positive. Okay, I think someone is using annotation. Uh, Please, whoever is using that one, stop that. I don't know how I can do it from here.
Sir, you can go to edit and there is an option annotate
Uh,
on or off. Please check it,
where
sir.
I get the edit?
At the top, sir.
This one, right?
After file, sir. Yeah. No, no, sir. In the WebEx one, in the WebEx
Uh,
window, beside
You have upper, there is annotation tool on the top left.
okay, top left.
Somewhere there will be a scribble kind of a thing.
No, I don't have one scribble. Is this one only I have?
No, not inside the tabs.
not in this
Outside
screen,
it,
sir.
or no, outside SAP. Or reshare, just reshare, it will go out.
Okay, okay, I'll do that. Someone is asking for approval of annotation. Please don't do that, whoever is asking for that. Okay, it was here, top ribbon. Okay, fine, we can continue. So you have the compression force as axial force. You can give it as minus, for example, 1000 kilonewton. So I am defining in terms of Newton mm centigrade like that. So it will be 1000 Newton. Sorry, 10 lakhs Newton. Okay. So after doing this one, you just click somewhere outside this box. You will get the update of this moment curvature curve. Okay. So
Nigel,
like this,
small question. What is the blue dot?
blue dot is the, I think this is performance level, some kind of. Let me check.
Okay. Yeah, sure. Thank you.
This is the performance level, but I don't know what exact performance level of that. Okay.
So this blue dot is strain of confined concrete.
It's like capping stiffness.
Yeah,
Strain of
that is
confined
what
concrete.
some performance level it is showing. Okay,
Sir, one question, sir. Here the curvature is not failing.
sorry. Yeah,
Curvature
could
is
you?
not failing, sir. It is going straight.
No, no, you just look at these values. Okay, this is in terms of 10 to the power minus 6. Okay,
Mm.
so this much is shown here. Don't go by this shape. Once you plot in Excel sheet and you take the range, how much is important to you, you may get different shape. So uh, considering the range from 0 to this one, it is showing like this. Okay, don't go by this interpretation. Okay.
So, sir, from here, what is the failure criteria?
Failure criterion strain, stress strain curve.
No, in the MP curve.
Strain stress curve only what, sir? Here the strain which is coming for
Mhm.
blue dot the confined concrete, and when we go at the end of this curvature, it is showing some steel is reaching up to the maximum strain. So it
I
means
think
what
the
is the
question, see, here it is in terms of movement and curvature. Okay. In horizontal axis, you do not have the strain, it is curvature.
but the strain is showing at the right, sir. At the
Yeah,
right
if you look at
diagram,
the
it is
strain
showing stress.
diagram, when you go along the Amphi curve, you can see values of strain are changing. So I think as Taijul said, if you
Yeah,
look at the
yeah.
values
Here,
into Excel,
here you can see
you
strain. You have to see here. Okay, when I am moving my cursor here, the strain variation you can see here. Okay, for concrete as well as for steel. And see this so regarding strain, we will discuss. Okay, you'll come to know. We'll discuss all these things. And don't
No,
go by this
sir.
interpretation. Don't go by
My
this
क्वेश्चन
interpretation.
इज सर आई एम नॉट सेइंग सर सर मेरा क्वेश्चन ये है सर कि यहाँ पे
Mhm.
फेलियर क्राइटेरिया क्या ले रहा है कि कन्फाइनमेंट का हुप है वो ओपन हो रहा है कन्फाइंड कंक्रीट फेल हो रहा है कवर कंक्रीट फेल हो रहा है क्या फेल हो रहा है जिसको ये फेलियर क्राइटेरिया मान रहा है
Sir, this is not failure criteria actually. This is not showing any failure criteria. This is just a curve of your section. You have given some section as input. It is showing the overall capacity from zero to maximum, whatever capacity it has. Now you have to decide at what point you have to consider this as a failure. Okay, that we'll discuss. But this is not showing. Actually, I don't know exactly what it is showing. I have to verify this one. Okay. But don't
वन
compare
मोर
this
थिंग
with the
सर
failure. That is different thing
सर
that we'll discuss.
सर कभी कभी जब हम मोमेंट कर्वेचर बनाते हैं सेक्शन
हाँ.
डिजाइनर में तो वो
Mm-hmm.
नीचे की तरफ मूव करता है लास्ट
Yes.
पॉइंट के बाद यहाँ पे मूव नहीं किया है तो वो जो मूव जिस पॉइंट से नीचे की तरफ करता है उस पॉइंट को क्या माना जाए
Yeah,
जैसे
that's what
आपने भी
I,
बनाया होगा तो आया होगा
sir, will discuss. Please wait for a moment. We'll discuss that. Okay.
ओके सर
I am telling you just copy this data and plot in Excel. You'll get some different shape. Okay. Don't go by this interpretation. Okay. So this section is already created. That's why I didn't save this one. And you see the shape here. Here you see I was talking about this one, blue shape, as sir currently right now asked why it is going flat. Okay, this curvature is up to 0.0001. Okay, and at this point you just check what is the strain value of that one. That you will get to know from this analysis again. For getting this curvature, what was the actual strain in your steel and what was the actual strain in your concrete? Okay, that parameter you can note down. Now software is giving some flat region. This to verify this flat region, why it is giving, you have to first find out what is the strain at this level, at this curvature level. Okay, so you analyze the section and at this curvature find out what is the strain here and what is the strain here. So once you get to know this, this much is the strain in steel and this much is the strain in concrete, then you go to this curve and verify at what point of stress strain curve it is. Okay, so this is what you have to do to understand whether it is failing or not failing.
सर जहां पर आपने जो मैक्सिमम अल्टीमेट स्ट्रेंथ कन्फाइंड कंक्रीट का लिया है 0.05
Mhm.
ये जो पीछे वाले डायग्राम में ये हर जगह तो सेम नहीं होगा 0.05
Yeah, it cannot be same. Depending on your section, it will be different. So that will be your ultimate movement, sorry, ultimate strain for that section. This is just an example. Some example I have taken from these shows. Seismic design of RC buildings by Jack Moyle. So this is just an example, okay? And this 0.05, this is permitted for steel in case of earthquake for Indian standard. Okay, you can use this 0.05 everywhere for steel if you are designing your building by Indian standard. Okay, but for concrete it can be different depending on the capacity of your actual section. But as you asked where it is, whether it is failing or not failing, I am telling this is the procedure you have to follow. You note down the curvature, then from this section analysis, determine at that curvature level what is the strain in steel and what is the strain in concrete. Okay. Then after finding out these two parameters, then go to this curve and compare at what level of this curve you have the strain. And based on this, you can now decide whether it is failing or not. Okay. But you have to be, means you should be understanding using this curve also. But the thing is, if you consider the moment curvature using this software, SAP or ETAPS, I do not find it reliable after crossing this limit. Means you can identify or you can determine the peak strength in terms of force. But if you want to determine the curvature using this software, then I do not find it reliable. That's why I do not use. But many people use. So I just want to explain what is the procedure of doing that one. Okay. So ultimate capacity in terms of curvature, I don't think you have to use using these software tools. But the strength you can follow. It is giving the reasonable value. Okay. And from this comparison also you can say using three different software, I was getting almost similar and initial slope also. Okay. So and one more thing important in your nonlinear analysis is this one only, this initial slope and the strain up to this peak region. Okay, after the after the post peak region, you can decide how much you want to go. Means we always try to be on the safer side, underestimate the actual strain capacity. Okay, so that region you can apply your consensus for determining the peak strain or peak curvature. Okay, but till the peak region, you can take from these tools. Okay, and we'll talk more about this one when we go further with our analysis or sessions. Okay, so this was using the SAP. Similarly, I'll show you
Sir,
now.
excuse me, sir.
Yes,
Excuse me, sir. Can you go to the back slide, sir? The previous slide.
this one,
Back. The previous.
this.
There. Sir, here you are saying this 0.05 is the maximum strain. Excuse me,
Yes,
sir.
yes,
And
yes.
this 0.05 you are saying the maximum strain. The maximum strain for what? Confined concrete, for steel, or for what?
This
0.05?
0.05. I am not saying this maximum strain. I am saying that this is the example shown. But if you talk about Indian code, it says that 0.05 can be considered as the maximum strain in case of steel when you are doing the analysis for earthquake. Okay.
So 0.05, if it is strain, so it
Yes.
means ki when we are giving the input in the SAP, so
Uh,
in place of strain,
uh,
when we are giving the strain for steel,
mhm.
14.5%, there we have to give the strain 0.05 at the
Yes,
time of
exactly.
input. So
Exactly.
when we will give 0.05, as per
Uh,
that the moment curvature will come. But in this example, I don't know ki what you had taken the strain because you had just off that part. Can you
which
go
one?
again? Then I will
In
SAP
software? Okay, let me show. Yeah,
materials.
that you can decide. And I didn't edit most of the parameters here. You can decide that. This is 0.12.
Yeah. So
Okay.
here we have to give
Here
0.05.
you have to give 0.05 for steel.
0.05.
Yeah, 0.05.
So sir, can you move sir 0.05 and see the moment curvature?
Yes, of course we can do. So
Here it
here
is
it was.
down, getting down.
Yes. Now see. Yeah, it has. Of course, it has changed, and it will depend on. Obviously, it will depend on the strain, whatever strain capacity
So
you are giving. Okay.
sir, so,
And listen, please wait for a moment. When I go to the Python code, there I'll show you how you are defining that parameter. You will be more clear. Okay. So because in between, if you start discussing this question, maybe we'll not able to cover the session. Okay. So you just keep your question ready. Whenever we answer or we come to that point, you can ask. Okay.
okay sir.
Okay. So using SAP, we have shown. Then SAP ETAB is similar. I'll just open and show. No, I'll not discuss. Okay.
Hello,
Yes.
Sajid.
Yes.
Yeah, can't we put this question answer session at the end?
Yeah, that's what actually I also want to do. But people, if having questions, some immediate questions, so I just thought maybe one or two question we can take, but it should not be personal like you are asking one after the other. So that's why you just keep your question ready. We can discuss at the end, or else, as you have seen, we have prepared the question answer for last session and we have delivered it to you. Okay, in that way also you can ask, and I think that is the better option, because what happens when you ask the question and we answer, it just goes off. After that you may not be remembering some other people's if you want to ask same questions. So you just put your question in the question answer box and we'll try to cover all the questions. But yes, at the end of the session again we can discuss. 1 hour is there, we can discuss the question there also. Okay,
Yeah, thank you.
so this is the interface is similar to etabs. Sorry, similar to SAP. This is it. ETAB actually. Interface is similar to SAP. So I have created this section. Then again you define your parameters. Sorry, that's material option I have not shown. Actually, it was similar, that's why. So material option here, you define the materials. After defining, you go to your section. Then again, to define your sections, same thing, same as SAP. Okay. So after defining this one, so this curve is
Sir, your
here
screen
and you
is
can get.
frozen.
Sorry.
Your screen is not moving, it is still stuck.
There is
Okay.
lag.
Yeah, actually it may be because of the network. I think I'll wait for few seconds until you get to see. Let me know when the screen is coming. I am on the E tab and the section designer interface I have opened.
It's visible now. I think moment curvature plot is there on the screen.
Oh, it was earlier one. I have just closed that one. Maybe.
Section designer.
Yeah, you can see the section of means one cross section with reinforcement arranged, right?
Yes, yes.
Okay. So you click
Sir,
on the curve. Yes.
do from start, sir. The screen is lagging, so we cannot see that starting.
Okay. Fine. No problem. So I have opened ETAB. Then you define the material similar to what you do in SAP. Okay. Here I have defined M30 for concrete, Fe415 for steel, means transverse steels, and Fe500 for main steel. Okay. Again, these are all similar to SAP. You define these parameters here. But there is one change with the concrete that I think I have to show. This one. Earlier we have defined the expected strength as 0.8 into 0.85 into FCK was 30 plus 1.64 into sigma was 5. So it was coming out to be 25.976. But now here it is say 32.47. Okay. So this difference is coming because of this statement here. Here it is clearly written concrete cube compressive strength. So you have to define the strength with respect to the cube, not with respect to the cylinder. So the factor which we have multiplied to convert the strength from cube to cylinder should be ignored. Okay, and that was zero point 0.8. So that factor 0.8 should not be considered here. If you ignore that 0.8, you are getting 32.47. Okay, so this is one of the important thing you have to take care of when you do the design using SAP, either SAP or ETABS. Okay. Okay, fine. Next, we can go to the section, and this is the section we have created. And this is the section. You just right click anywhere and you can get these details. Again, you have height, width, then reinforcing, yes, 12 number of bars, and you define the tie bar 10 diameter and corner bar and edge bar like this. Okay, and same thing you can do here also by right clicking. Whatever you have done in SAP, same thing you can do here also. Okay, so this is how you create the section in ETABS, and again click on this option, so it gives you the moment curvature. Okay, and here also it is written axial force P in tension positive. Now, if I want to give in compression terms, so I have to use negative term. Sorry, it is clearly written in kilonewton. Okay, so you have to give only whatever in kilonewton, that much. Now see, and once again I am telling, don't go by this shape interpretation. Okay, you just copy this data in Excel and you take only the range what you need. Okay, don't go by this whole interpretation, shape interpretation. Here you have, when you show that, click on show table, then you get this information. Just copy this in Excel. Okay, okay, I got this one, so let me see what it is giving.
Sir, in ETABS, it does not give the option of inputting all the parameters like you did in
Yeah,
SAP.
that's what actually I thought I'll just explain this now. You already raised this question. Yeah, ETAB is not giving, but there is one catch. If you see here, don't you think this all the curves are in the similar range of strength up to this peak point? ETAB is not giving you, but I don't know exactly what ETAB does, because it doesn't know how much reinforcement, shear reinforcement I have provided, what is the spacing I have provided, and how many legs are there. ETAB doesn't know all these things, but still it gives the values which is matching with the others. Okay, maybe for means coincidentally in this case, because it was only two-legged, maybe by default it has considered two legs, so it is matching. So if you want to determine moment curvature for a, let's say, shear wall which is having multiple number of legs, so at that point may not be, it will give good result. Okay, so ETAB is, in this aspect it is unreliable definitely. Okay, because you do not know how it is considering, but you have some control in SAP, you have full control in STKO, and of course you have control in your manual calculation. Although here it is not matching, maybe because of I have done some mistakes in the parameter definition, so that I have to look again. So you have full control when you do manually, you have full control, almost full control when you use the STKO. Okay, so I'll show you.
Sir, excuse me, sir.
Yes, please.
हेलो सर, इन ई टैब में सर क्या हम वहाँ पे जो मेंबर प्रॉपर्टी डिफाइन करके कन्वर्ट एज अ सेक्शन डिजाइनर करके वहाँ से
Mhm.
कंट्रोल कर सकते हैं इसको?
Yeah, you can define the section in section designer, then you can use that section in modeling. You can use that.
नो नो नो, माय क्वेश्चन सर, हम डिफाइन कर ले सेक्शन को
Hmm.
जनरल तरीके से
Hmm.
और उसको कन्वर्ट एज अ सेक्शन डिजाइनर करके वहाँ पे कंट्रोल कर ले।
No, in section designer, what control you want to do? I don't understand actually.
Confinement effect, sir.
In ETAB, you cannot do because it is not giving you that option. In SAP, it was
Sir,
giving.
I'm not saying that, sir. Can you go to define? And then section property,
Okay.
frame section.
Okay. Define section property, frame section. Okay. 1 minute.
And then no section designer, sir. Just define some, just cancel and define some section, sir.
In section designer.
Not go to the section. No section designer, sir. Please cut, sir. Add new property, sir. Add new section, sir.
Okay. Add new property.
Sir, cancel it, sir. Add new section, sir. Sir,
Yeah.
your slide is not moving, sir. I think it is again stuck.
1 minute. Don't know. This evening time it happens. Network becomes very slow. Can you see something now in the screen?
No,
Except
no, sir.
interface. Okay.
It is stuck, sir.
So I think what sir means to say is in the list of all the sections that we have defined, on the right side there is
Uh-huh.
an option convert to SD section. So we define a general section with all the
Okay.
reinforcements and
Okay.
we give it as a command as convert to SD section and then we go to section designer. So is it a preferable option or not?
That
Rather
actually I
than just
personally
modeling the
didn't.
section from scratch.
Okay, maybe you can do, but I personally didn't use that one, so I would not like to comment on that. Okay, maybe you can do that. If option is there, it is to use, right? You can do that, but I don't know how it is actually acting. I have to look at it.
सर बिल्ट अप सेक्शन के लिए मोमेंट कर्वेचर का ऑप्शन ओपन नहीं होता है, इसके पीछे का रीजन क्या है? जब भी हम बिल्ट अप सेक्शन डिजाइनर के थ्रू करते हैं तो उस जगह उस टाइम पे मोमेंट कर्वेचर एक्टिवेट नहीं होता है।
That issue may be with the software. It should give, right? If you have some section, either it is steel section or concrete section, you have some section and some stress strain property, and you have the whatever logic we have shown here. This logic is already implemented in the software, so definitely it should give. Now software is not giving means there is some issue with the software.
ओके सर।
Okay. Okay, so this was using ETABS. Then let's see with the STKO. So here in STKO, you have 1 month trial, which you can use with the full features available. But after 1 month, suppose you do not take your license, still it will be free. But the number of nodes you can define is limited to 1,000. Okay. So I am doing the same thing. I am just defining one element, which is just 2 nodes. Okay. So up to 1,000 nodes, whatever element you have, you can use in that free version. Okay. But suppose you want to model a complete building in STQO, so this will not be enough. 1,000 nodes will not be enough. Okay. Okay. So what we do here is I have already one section defined here, but I'll just briefly go through what we have done. Okay. Let me first copy this one so that I can use it later. Okay, so we were discussing about this STQ, how you can model. This model we have prepared in X and Z axis. Okay, you can see this axis is X and this axis is Z. Okay, and this blue color is showing Y axis. Okay, so I'll take the same axis and you can just take this line, and I have to show this grid option. Maybe I can try here just to show you how it works. Okay, you just take one line. Okay, so this geometry is defined. Now you go to physical properties. Sorry, before going to physical properties, you define some kind of load pattern. Okay, now I'll define just a ramp load or linear load, you can say. You can define this one. So already one similar is defined here. Okay, then you go to physical properties, you add, and here you choose materials, uniaxial, and you have lot of options here, unlike SAP or ETAPS where you get only one or two materials for concrete and steel. But here you see you have lot of different materials. And I also feel that when I try to find some materials, it's very much difficult to identify at which option it is available. That many options you have actually. So you go to concrete 01. This is just an example, and you can explore what are the other material types does. Okay. Then what I did is it was M30. So here compression is negative. You have to give minus. Then minus strain corresponding to peak strength. Then you have ultimate strength. Let's say -6. Then you have ultimate strain. Okay. So you can define it in the range of 0.0035 to 0.005 or 0.006. Okay, so let's say 0.005, and you can test here how your material looks like. Okay, use the monotonic loading, then strain up to this much. We have actually defined up to 0.005, and you can click on this test button. Okay, so this is the stress strain curve for your unconfined concrete. Okay, then click on this. Your section is, sorry, material is defined. So similarly, you can define steel. Same, click on this, then right click, add. Okay, go to steel, uniaxial, and there are again different options. I have taken this steel too. So what each of these option do, you can explore and see. Okay, so our steel definition was 500, and this is the property of this model particularly. Okay, whatever I am defining, 925. This was 0.06 or something. I forgot. Let me see this. Sorry, this was 0.15. Okay, sorry. Here I have to use the expected properties. I forgot that. So this was 550. And see, if you get some different value, don't bother about this one, okay? Because control is with you. When you are defining your material, you have the logic I have given already. You use that expression, and whatever you are getting, you can use that. Don't worry about what I am showing here. 0.925, 0.15. Okay. So now you can test this also to see how it reacts with the strain. Let's say I want to give up to 0.01 and test. Okay, what happened? Oh, sorry, I didn't define this one. This is the Young modulus for steel. Okay, now you see. So it's basically a bilinear model with no strain hardening. Now, if you define this one, and you can see now you have linear strain hardening. Okay, so now to understand these parameters, what it does, you can just play with these parameters and see how it changes its behavior. Okay, so this is also a control. You have to understand how each of these parameter acts. Okay, So you define this still. Next, currently we are using a fiber section, so I'll have to also define a fiber. For that, you need to go to section, then use rectangular fiber section, and this is the fiber showing here with some default section dimensions. Okay, so our section was I didn't remember. So just randomly take maybe 400 by 400, and cover is 20. Here you have corner diameter of bars 25 and edge diameter 20, and number of edge bar was 2. This is also 20, then 2, 20, 2, 20, 2. Fine. Okay. So here you see whatever you are defining here, immediately it shows here. Okay. And this for concrete core. Okay. So none. When you choose none, it will consider confinement effect automatically. Okay, you don't have to do anything here. But if you define some parameters, so it will not automatically consider the confinement. You have to define manually the stress strain curve of confined concrete. That's why this option, if you want software to consider the confinement automatically, it should be none. Okay. Then this is for the outer portion of the core. Okay, so which is not confined. Here we define this material, whatever we have defined. Okay, and you see here, this blue line is showing the unconfined concrete stress strain curve, and this some kind of purple line or source, whatever, it is showing the confined concrete. Okay, and similarly we define for steel, and stirrups diameter, let's say it was 10 mm, and the spacing of stirrups was 150, two leg by two leg, and it was FE 415. So again 415 multiplied with the factor for expected properties. So whatever you are getting, 415 into something 456. Okay, so your fiber section is also defined. Now once you define your fiber section, that section should be assigned to this. Okay, so before that you have to assemble your fiber section with some integration procedure. Okay, so when you talk about this finite element concept, okay, so it does the integration at some integration points. So that integration procedure you have to define here. So at the moment I have defined this one integration Lobato integration scheme, which is available in OpenSys. Then here you choose what section should be considered for doing this integration. So I have defined that fiber section which is already there. Then minimum number of integration points you have to define here. How many integration points you want? Okay, at the point, since I am doing a section analysis, so I need only one cross section. So I have defined minimum 2 sections should be defined here. You can go for higher numbers, but just for section analysis you do not need 2 points are enough. Okay, and here also you have different kinds of integration options. So I have by default it is standard integration, so I have kept here this one only. Okay, now this is defined. So what you can do is you just select this element whatever is defined here in the geometry, then click on this and drag it. Okay, so this is defined. Now see, the physical properties we have defined, but what about the material properties or element, how the element behavior is going to act in the OpenSys analysis? Okay, that you have to do here, element properties. Go to element, add, again you have similar options. Okay, and here you have beam column, and I think I have chosen this force beam column or displacement beam column. You have options available for that. Let me check which option I have chosen. It is displacement beam column. So you go to that option, beam column elements, then you have displacement beam column. Okay, so after that this by default whatever is there you can choose. Just this element should be defined, no need to modify anything. Okay, now again after defining this, you click on this and just drag it. Okay, so element properties is defined. Now this element property, as you go by this name, displacement beam, means it is doing the analysis based on displacement control mode. Okay. Similarly, when you define force control, it will be doing the analysis in force control mode. Okay. So after that, you define the support conditions and other constraints available. So you have the condition option for that. Right click on that and add. Okay. First, we'll define the fixed option, means fixed support condition, constraint, single point, and fix. And consider 3D and displacement and rotation, and which degree of freedom you want to fix. So I want to fix all. Okay. So it is defined. Then similarly, you have pinned other end. Okay, because I will be doing the displacement control analysis, so I should control the constraint of this point. So I have to pin whatever direction I do not want. Only the direction I want it to move, I will release that one. Okay, so you can see here I have pinned UZ. I do not want any movement in Z direction. I do not want any movement about X axis. I do not want any movement, means rotation about Y axis. Okay, that I have pinned because my rotation, I will be applying the rotation this RZ. My applied rotation will be in this. So I have released this one. So because of this rotation, I am also allowing the displacement in X axis and displacement in Y axis. Although Y axis you can again pin, no problem, but it doesn't matter. Okay. Then you apply the axial force, whatever you have. So in this example, the axial force was 1435 kilonewton. That much I have defined, and you apply the rotation. Okay, and see, as I said, along this direction I have applied the rotation, and this again, how much you want to apply, you can apply. I have applied 0.0025 radian per radian rotation. Okay, so this actually last two I have not shown how you have to define. So this is same procedure. You just go and find out where this option is available and you define that one. Okay. Now, once you have done this one, what you have to do, you just click on this again and select the point where you want to apply this. Okay. So I want to apply this fixed point here. So I have just clicked this one and okay, it is applied. Then you go to this option. At what point you apply this one? Pinned other. So this is the other point what I want to pin. Then go to axial force. I want to apply this. The directions are already defined, so don't have to worry about this one. And again, this one, applied rotation, I want to apply at this point only. Okay. So everything is done. Now you have to arrange the sequence, and algorithm you have to select which will do the analysis. Okay, so in STQ you have MPCU recorder, which actually controls the nonlinear or whatever, means numerical computation. It take care of that. Okay, so you go to analysis steps, then add and recorders. Select MPCU recorder, and here the parameters what you want as output, that you can decide here. I want, and it is also showing at what point unit I need the nodal result. Displacement I want, rotation I want, then you want the reaction force, you want the reaction moment, and whatever you want you can select. Then I want also the element forces, I want element deformation, then I want section forces, I want section deformation, then I want material stress, I want material strain, and section fiber stresses, fiber strain, whatever you want you can choose here, and this can be deferred, no problems. Okay, then you add the constraints. So this is like a sequence of your analysis as you do constructions, stage analysis. So you define some stages by following which you have to do the analysis. Here also you have to do. After defining the geometry, you have to add the constraint. Whatever constraint we have defined, now our first step is to use those constraint in the structure. Okay, so you use this add constraint option, and you click on this one, single point, because we are defining this constraint at a single point. That's why you have single point and multi-point option. Suppose you have more than one point, that time you have to go for this multi-point. Okay, so you click on this, and here you see what I am doing at this step. I am defining two parameters at this step at the same time. Okay, so initially what happens, it will be 0, nothing will be visible here, so you have to click. Now I have clicked, I have two options. I have to define the fixed end, and I have to define the pin end. I have done these two steps at the same time. Okay, but if you think you have to do it sequentially one after the other, you can do that one. It depends on how actually your structure is going to be analyzed. Okay, so next, after adding the constraint, you next add the axial load. Okay, and for adding the axial load, I have used the linear or ramp time series, whatever I have defined at the initial stage. Then what is written here, load, how much load you have to add, and at what point. Again, so it will be 0 by default, you have to click 1, and if you have more than one load, you have to just increase this number. Okay, so I have one load, which is axial load, I have selected here, and okay. See, right now already everything is defined. That's why I'm canceling after defining. But in your case, when you are doing this for first time, you have to assign this, not cancel. Okay. So once your actual load is added, then you start analyzing the structure for that load. So you have to add this actual load analysis. This also you'll get from this option. Right click, add, and select your analysis and analysis command. So here you have all the things. Now whatever I have defined, I'll show you. See, this is a static analysis, and this is some constraint transformation method. You can explore in the OpenSys manual. I also not very much clear about how this does inside. Okay, so these are some numerical parameters you have to define here, and here you have algorithm, which algorithm you want to use for your analysis. Okay, and you can go for normal displacement increment test or normal unbalanced test. All these parameters you can explore actually. I am also learning this software for last few months, so I have some control with this, but not very much, so that I can give you a full explanation of that one. Okay, you can go through all this. And here it is load control. Okay. Okay, so that's all you have to define. This is for one load case, which is gravity load case. Similarly, you have lateral load also. For that, you again go to your lateral or rotation, whatever, maybe lateral displacement or lateral force, whatever. And I am using the same time series. You can have different time series also. For example, suppose you have earthquake load, which is in terms of time history. So in that case, you cannot use this linear time series here. So that time series you have to define at the beginning, and the appropriate time series you have to select from this drop down. But in this case, since this is a simple static analysis, so I can use the same linear time series, no problem. And again, it is a single point load, so I have to go to this single point and apply this rotation. Then cancel, because already I have that, so I have cancelled. So after applying the rotation, so you start analysis again. This is same analysis step what I have shown earlier. Okay, fine. This step is repeated, so I'll remove this one. So now your parameters are defined, everything, your analysis steps are defined. Whatever I have defined newly, I'll remove all this, because otherwise it will show some error in the analysis. Fine. Now see, here you have to define your mesh. This element, how many number of division you want to make in meshing. Okay, since this is a small element, I do not want any meshing. Maybe only one single element will be enough. But if you want, suppose I want to divide this into 5 number of elements, So you can go to this one, you can define number of division here, and it will show 5 nodes here in between. So that you can do. Then once your mesh is done, you just have to click on this build mesh. Okay, then that software will consider the mesh you have defined. So after that, you go to your analysis, and software has 3 options for analysis: OpenSys, then OpenSys multi-point, OpenSys single point. At the moment, I do not know what actually these other 2 options are doing, because I haven't explored this. So I just used this one, and you can also use same thing. This is just done to show you how we create the model. I delete this one. Already it is created, right? So I'll just show the analysis steps, and this is showing where output result should be saved. So what we can do, we can click on this folder. Lines haven't been matched. Okay, this is showing some error because we have edited, maybe somewhere some error occurred. So I'll use the saved model previously. This was the original model. Okay, everything is done. Just you click on this build mesh and run your analysis. So your analysis is done, and go to post processor. You just call that output wherever you have saved from that folder. Okay, so it is showing one section, whatever section we have created, that one. And I do not want this solid geometry, I just want to see the fibers. Okay, so this you can do by clicking on this option, and this surface I'll delete. Now you can see the fiber. Okay, and I want to also show the nodes here. See, there are 2 nodes as we have defined earlier, 2 nodes in the integration scheme. Now you have to plot the chart. Go to extract. I want the values at the nodes, then click on that, and at what option. See, there are 2 stages of analysis as we have done. We have defined one stage for gravity analysis, means for axial load, another one for lateral rotation. So I want the result for second stage only. Then in terms of what? In terms of rotation about z axis, and in terms of moment about mz axis. Then next, and you define at what node I want this. So I want at this node. Next, next, and it is giving you a nice curve. Let's see what this looks like. Control all and copy. You can just plot it. Okay, so for whatever range of rotation you have given, so it is showing flat region for that. So again, here I want to emphasize that point. Do not go by the interpretation of shape. You just consider the range, how much is important to you. Okay.
Can I ask
Fine.
a question?
Yeah, please.
Yeah, so this infinite ductility that we
Yes.
can see in this curve,
Mm-hmm.
if we measure the curvature ductility, which will be very, very
Yes,
high,
yes,
which
yes,
we can never achieve.
yes.
So how can we limit that? Means based on what inference or what uh, measure we should use
Yeah.
to limit it?
Actually, here what control you have is, let me go to material definition. The control what you have is here. Okay, you have definition of ultimate strain, definition of peak strain, and another control here. But other than this, you do not have any control here. So I don't know what actually software does to give this ultimate ductility actually. But when you do manually, as I have shown in my presentation, suppose you go by this. Although here some mistakes maybe probably I have to rectify this one, but it is going down. So it will come like this. So when you do manually, you have full control. You can do that. But software, I don't know. They have designed the software. What parameters they have considered, I do not have any idea. So that's why I'm saying in when you are determining movement curvature from software, you consider only up to the peak point where you have the peak force and the whatever in horizontal axis, either strain or curvature. Don't go beyond this peak point. After that, you have to make your own judgment for that portion. So that's why I always use the manual calculation. Okay, and in this software, what you get is one peak strength, another one initial this one stiffness. These two parameters are correct, as you can see from this validation. All the four different procedure what I have followed, almost same stiffness and almost same peak strength. Okay, so you can consider up to this point by the software, but remaining portion I don't know why software does this ultimate strain capability or curvature capability.
Maybe shear is not captured in that.
Yeah,
The
but
moment will also
here,
generate the shear, but that shear demand is not, capacity is not addressed. That's
yeah,
why
can be.
unlimited
So
movement.
this you can only verify by trying with different options. Suppose you model your shear and you check the result and compare with the one which is not considering shear. So like this is just experimentation process with the software. Okay. So I didn't do this. So I don't know at the moment. Maybe if when I do, I'll get some idea and I can share. Okay, fine. So we can move further. Let me close this one. And sorry, one more thing I forgot to show here what else you can do. I am actually running out of time. That I'll show later when I get some time after that because there are some important things I want to discuss. So already you had some idea, different softwares, how they give movement curvature and this manual one. So I forgot this one. Let me open this. I'll go fast with this. Okay, so this code is already prepared. See, this is a nice, not nice actually. Many of you will not like because this is very much lengthy. But here the important thing is the idea of what you have, not the code, because this code will act how you imagine it. I have imagined, so I have prepared in this structure, but it may not be like same structure you'll have in your mind. So only important thing is what idea you are generating in your mind, and this idea will come from these two things. One is this one, and another one is this one. Once you have the understanding of this concept, how it actually does the things, once you have the idea of that and once you understand these testing properties, okay, then this idea will be automatically created in your mind. So I think many people, they whoever have not used any programming, they have that intention in mind that, oh, this is programming, I cannot do that. It's not like that, because I also did not use the programming till before one year. For the last 1 year, I am trying, and I have so far created I think around 20 or 30 programs for my research purpose. So it doesn't matter whether you have used it or not. Just you have some idea and you want to implement it. Maybe some commands you have to learn, which is for each software or each programming language. Okay. So this I'm not going to explain because already I have explained here. These things I have done, I have implemented in this program, but I'll just give you a brief idea of how Python works. Before that, let me show you how this works. Okay, and for that I have to wait for some time because of this. I'll increase this tolerance so that it runs fast. Okay, let me run this. So it is asking enter the ratio of design strength to the yield strength. So this I have created as per our Indian standard. So it should supposed to be 0.87, but since I am doing the analysis based on expected properties, I'll use it as 1. Okay. Similarly, asking for transverse reinforcement also, and the shape it is asking, shape was rectangular or whatever shape you have. And it is asking for cube or cylinder. So let me say cube. And what is the standard deviation? So for concrete it is 5, and enter the axial force 1000 kilonewton. So it will run now, and here you can see as it is running, what is actually going on at different strain levels. So at this point, it has considered some strain, and it has satisfied that equilibrium condition C is equal to T, and it has highlighted that strain. Then it goes to next point, again do the same thing, go to next point, again do the same thing. So it is keep on iterating based on this procedure. Okay, so leave this in background, and we'll come into this point once it is completed. Okay. And regarding this Python, how the Python works, I have another basic code that I'll discuss at the end. It will take maybe 5 minutes. So whoever is interested, they can listen. Okay. Next, the very important thing when you do the modeling using any software, either SAP or ETAP or StatPro or whatever. Okay. To understand the degree of freedom, different degrees of freedom corresponding to different types of elements. So here I have comparison of two elements. One is frame element, another one is shell element, and these degrees of freedoms are defined with respect to etaps. In etaps, you see for frame element, it defines the first degree of freedom along the axis, then second degree of freedom like that, and third degree of freedom means x, y, z like this. Now this you compare with shell element, it is little bit different. See, in shell element, your degrees of freedoms are defined like this: x, y, z. Z axis is similar in both the cases, but not x and y. Okay, so when you are using your like frame a shell element for modeling and you are defining the stiffness modifiers, you have to take care of these degrees of freedom. Okay, and I am also going to teach how you can model your shear wall using this frame element. And that point, I think most of the people will get confused because you want to use the shell this element, but you do not want to use the degree of freedom defined for shell element. So that should be avoided. Otherwise, your model will not be correct. Okay. Now see, this is for shell element, whatever degrees of freedom. So this you consider as a base and consider one shell is going up like that. So you have x-axis, you have y-axis, and you have z-axis coming out of the plane. Okay, and it is showing the forces along x, forces along y, and forces along z, which is coming out of the plate. You cannot see, and similarly rotation or movement here. Okay, so to explain this, how it actually interprets the different stresses, I have done this. You can imagine here. So you have first axis, second axis, and third axis. Corresponding to this first axis, you have stress F11. This F11 you'll get when you go to define the stiffness modifiers for shell element. Okay, so this is the meaning actually for F11. The first number is showing the direction, means along this direction, and the second number is showing the plane. So this is also acting in this first plane. That's why it is F11. Then second one, again first number is showing direction and second number is showing the plane. And similarly, you have F33 if suppose it is available. Here it is not there. Okay, and now see, this F22 and this F22 both are same stress actually, acting along the vertical direction, but originating because of different action. This F22 is because of the axial stress, sorry, axial force, but this F22 may be because of moment, some bending moment you have applied because of that. But when you interpret this in terms of stress, it becomes same. This will be important when you are defining the parameter. This will come to know after few more slides. Next, see in this slide, again you have F22. This is because of in-plane bending. And again you have F22. This is because of outer plane bending. But the direction is same. If you compare these two cases with these two cases, these are same. So these things you have to keep in mind. Then see moments M11 and M22, whatever is defined here, M11. Actually, this interpretation is wrong according to our understanding. Because when I have tested, validated this frame model with the shell elements, whatever interpretation is given here, it was not acting. Then I have done some trials and found out that this is the definition actually. Okay. So this M11 means you have one column and you are trying to bend about the vertical axis. You can imagine like that. Okay. Then you have M22. This the column, whole column or whole shear wall you are trying to bend about the horizontal axis. So this is going to be your M22, and you have shear. You have shear along V13, which is again direction is 1 and in plane 3, and this is V23 direction 2 and plane 3, and this is F12 direction 1 and plane 2. Okay, so this from the this uh, what do you say, F12 is going to be equal to F21 and V23 is going to be equal to V32, like that. Okay, I forgot the term what we call this one. Okay, now see, this table is going to be important when you want to define your shell element using frame element, because in frame element you will get these parameters for defining your stiffness modifiers, not these, but you have to define this for shear wall, right? So that's why this comparison, it will play a big role when you want to model your shell element using frame. So in frame element you get I22, but now if you define I22 in shell element, what actually it will do? It will modify your axial stress as we have explained in earlier slides, and it will also modify this M11 and M22. But it doesn't matter. I'll tell you few more slides later why it doesn't matter. So I22 you can define in case of shell element model by frame element. Then moment of inertia I33. When you define this, again it is going to modify your F22. It means when actually want to do F22 modification for shear wall, you have to modify this I22 as well as I33. But in case of column, what we do, if I consider I22 as my in plane, but I33 will be my outer plane. So I ignore my outer plane, maybe. Or else, if it is for other direction, if it is column, I will consider both the axes. But here in case of shear wall, it is not like that. You have the understanding that in shear wall, we do not consider outer plane. But so thinking that one, you may be ignoring this one, but it is not correct. You have to define this because it is ultimately going to affect this F22. Okay. Then in frame, you define shear area in two direction. This is corresponding to F12 in plane shear in case of shell element. Then you have shear area in three direction, which is again going to be for outer plane. This you can ignore because this is outer plane for shear wall. Okay. And corresponding to this F11, there is nothing in frame element. So you can simply ignore that one. And moment of inertia I22, as I said, this is also representing this M11 and M22, and these are again going to be outer plane. So you can ignore this one, but here you cannot ignore. So what you can do is you can define some smaller values here, or you can define higher values also. It doesn't matter because outer plane, so automatically it will get compromised there. Then corresponding to this one also there is nothing, so you cannot define that one. Okay. Then this is crack section properties, whatever we have discussed here. In case of your analysis model in ETABS or SAP, you have to define crack section properties. The concept is your concrete gets cracked when it reaches the flexural strength of concrete. Let's say this horizontal load in terms of deformation I have applied here. So what will happen? This member will go for deformation. Once this deformation reaches a limit where the stress at the base portion of concrete reaches the flexural stress, then it will get cracked. Okay. Then as the analysis goes on, the cracking will occur at other portions also. So at that point, that concrete will get cracked. Okay. After cracking the cross section, what you have considered for gross moment of inertia doesn't is no more valid because it is reduced cross section now. So to consider this effect, actually we define these stiffness modifiers based on experimentation done on large number of models. Uh, the code people have come up with some values, approximate values that you can use. But we'll try to see with a practical example. And before that, again, this is done with this example column actually. And here you see what I have done. First model I have done, which is in blue color, distributed fiber plasticity, means this whole cross section is considered as non-linear. I have distributed and modeled is using fiber at different points. So non-linearity is considered in the whole section, and I do not have to use any crack section in this case. Then another orange line is there, which is finite length fiber hinge. Means this is also fiber section, but nonlinearity is considered only at the bottom and at the top. Intermediate portion is considered as elastic. So in this case, I have to consider the crack section for the intermediate portion. Then I have considered the moment rotation hinge. Considering the uncorrect section, means I did not consider any stiffness modifiers. I have considered the gross moment of inertia, and this is the curve you can see. Okay. Then next is moment rotation hinge using the crack section properties, and you can see this is merged with the fiber section of continuum means distributed plasticity or finite length plasticity. Now what I want to say here is the importance of crack section is this one only. When you consider the whole section is nonlinear, although this middle section do not go into nonlinear range very much, but still some kinds of nonlinearity or some kinds of action will be there inside this middle portion. So when you consider this as a nonlinear case, automatically it is considered. You do not have to explicitly define the crack section. But what if when you define the nonlinearity only at each endpoint, either at top and bottom, intermediate point have full elastic. It do not have any failure. It do not have any cracking. It do not have any damage. So it is overestimating the capacity at the intermediate region, which is also affecting your overall behavior. So to take into account, we define this approximate stiffness modifiers. And from this example, you can understand if you do not use that modifiers, what will happen. So final means originally your capacity should be this one, but once you consider the gross section property, your capacity is going to be this one. So you are overestimating the stiffness of your section. Okay. So this is the case. That's why we go for the crack section properties. I think this is clear. Actually, I wanted to show this example again in STQ, but I don't think there is enough time. So I'll skip at the end. If I have time, I'll show this one.
Sorry to interrupt. Are these results from some research paper?
This is, you can say this is my research actually. I have done, not from a paper. So if I publish this paper, yeah, you can say that time it is from paper. But at the moment, it is part of research.
Okay.
And this, whatever models I have used for this, I will be sharing all the models. You can do whatever experimentation you want to do with this. Okay. All the models, ETAP, SAP, STQ, everything I will be sharing. Now see, this is the crack section properties defined in our IS code, Indian standard. For beam, You have flexural stiffness consideration as 35% of gross inertia and shear 40% of EA. EA is the gross stiffness, shear stiffness I'm talking about. Similarly, for column, it is zero point 0.7, means 70%. For wall cracked again 70%, for wall cracked again, uncracked again 70%, and 40% in all the cases for shear stiffness. So here what I want to say is for column and shear wall, it is fixed irrespective of whatever axial load you apply or whatever section capacity or whatever reinforcement you have. Actually, this is not appropriate if I consider all those parameters. This you can understand from this example. This is as per ASC code 41. 1 minute. So for beam, it is given as 30%. Again, these all the values are based on experimentation. There may be some differences. For example, let's say in some member they got 30%, some member maybe they are getting 25, some member maybe 40. But based on a large number of experiments, they have come up with some value. Okay, so this is the median value of all those experimentation, 30%. Then
सर
instead of
स्लैब के लिए मॉडिफायर्स क्या है?
there is modifiers for slab also, but I didn't use here for this presentation. It is available, you can use. Okay, maybe at some other sessions we can take up this, but here I do not have these values to show. Okay, so in case of columns, according to ASC 4117, it also depends on the axial force. When your axial force ratio P by Ag into FC exceeds 70%, so you have to consider, sorry, this is not 70% actually, it's mistake.
This is 0.5.
Yeah,
Yeah.
it's 50%. So it is going to be 0.7, means 70% of the gross moment of inertia. And in case of column, which is having this ratio less than 10%, you have to use 30. In between that, code says you can use linear interpolation depending on this ratio. But again, here they have considered only axial force. Now, if you go to SCI 318, which is the concrete design code for USA, there they have expression which is also depending on the moment capacity and the percentage of reinforcement provided. It means your stiffness modifier is the function of your moment capacity, your tensile reinforcement, and the axial force. Okay, so that also you can use. Now see, after knowing all these things, whatever we have shown so far, you are finally going to define the stiffness modifiers for your frame elements. Here it is for column. So in case of frame element, I have to define only two parameters mostly. Moment of inertia about x-axis, about y-axis. Okay. So these values, what you see, this is as per this provision, not this one. So depending on the axial force, you get some value and you enter here. Then you have stiffness modifiers for shell element. And here I have seen people are doing mistake. This is the correct interpretation how you have to define the stiffness modifiers for shell. You have to define F11, you have to define F22, and as I was saying, this M11 and M22, I think I can show this one. This one. I told you are defining I22, but it is for outer plane. So although you are defining I22 for this purpose, but it is also representing this one. So what happens actually? It will happen because of this dimension. Since this dimension is very much negligible compared to the, sorry, this dimension compared to this dimension, so it will automatically be ignored when you're defining using the frame element. Okay, so I have defined I22 and I have defined I33 and cross-sectional area. Okay, and other outer plane you can ignore. Sorry, I was wrong here. So outer plane you define here and you ignore this one. And this F22, what I have told here, F22 will be considered using other I parameter. Okay, let's say this is in plane, so it will be considered by this one. and this you can use a negligible value to represent this one. Okay, so this will be represented by this one. So other this is I33, so you can give negligible value to represent M01 and M22. So this is when you are modeling your shear wall using frame element. This one you have to remember, this is important. But if you are not defining these parameters correctly, your structural behavior will be different. Okay. Then see, there are some other parameters which are important for modeling. One is offset, end offset. Another one is rigid zone factor. Okay, so these parameters are used to model the joint rigidity. When you connect your beam with the column, you have the joint, and the joint portion is more rigid compared to the other portion of the member. Okay, that's why this rigid zone factor you have to define how much rigid actually you're considering this. And end offset equal to half of the supporting length. It means this much portion of the length will be considering for this rigid zone, whatever you are defining. For this much length, it will be considering. Okay, and software automatically consider this as half length of your member. So it means half the cross sectional dimension. Then rigid zone factor 1 indicates it is fully rigid. So if you define this parameter as 1, the joint will be considered as fully rigid. There will be no failure irrespective of whatever load or moment you apply. Then 0 indicates it is fully flexible. But again, based on experimentation and observation in the past, they suggest you can use 0.5 for rigid zone factor in case of RC members. Okay. So it is not fully flexible, it is not fully rigid, in between that. For shear walls, this rigid zone factor should be used as 1, because what happens in case of shear wall, if you take this member, so the failure generally doesn't occur in this portion, it occurs in the portion of the beam which is supported on this shear wall. So this you consider more rigid compared to the beam portion. It's not like this is fully rigid overall, but it is fully rigid compared to the beam which is connected to this. That's why you have to use 1 here. Okay, and this parameter is not required when you are modeling your shell element using shear wall using shell element. It will be required when you are using the frame element for modeling shear wall. Okay, so this I'll show in the software how you define these parameters. But here what I want to say is this rigid zone factor is 0.5 for frame element modeling, not for shear wall, for beam and column, and 1 for shear wall when you are modeling using frame element. Okay, so finally, what option you have for modeling shear wall in ETAPS? You have two options, as I said. You can model using this frame element or white column concept, or you can use shell element concept. But when you use this white column concept, the advantage you have is already there are some hinge model available in the software which you can use for nonlinear modeling. But there is also a hinge model available for shell element, but that is not that much capable compared to, or that much explicit, where you can define the parameters as how you want. Okay, so that is available in case of frame element. That's why we want to use the frame element instead of using the shell element. Okay. Then shell element modeling is sensitive to meshing. This is also one of the factors you have to remember. When you are modeling your shear wall using shell element and you are not defining your meshing properly, the result what you get may be very much erroneous. Okay, so there is a work before modeling this one which you have to do, and that is to validate your mesh. Okay, once you do this validation, then you are okay to use that, no problem, but you have to do that. Next is when you are using shell element, one thing is meshing, another thing is you have to use horizontal rigid link which is needed to connect the beam for providing joint rigidity. Actually, whatever we have uh, means known so far, In industry, they do not use this one. They just use the shell element and directly connect the beam with shell element, and without knowing what is actually going to happen, how it is interacting, how the forces are transferred, and how it is distributed. They do not think about all those things. So in that case, what happens is your behavior is completely different compared to what it's supposed to be. Okay. So please remember, when you model using shell element, there is no restriction. You can use that, but you have to take care of this. You have to take care of this. If you do not do, then your model is wrong. This I'll show. Okay. Then plastic behavior of shell element is modeled according to the material stress strain curve. So yeah, when you model your shell element, means shear wall using shell element, and it is divided into number of fibers, and each fiber is assigned with the stress strain curve. So that stress strain curve is also used for nonlinear analysis. Okay. Then there are two approaches for your hinge definition. You have one layered shell techniques where you do not need any hinge. That nonlinear layer itself will consider the behavior. And you have one elastic shell with plastic fiber. So we define the shell again. This is similar to frame element, and we explicitly define our hinges for considering the nonlinear behavior. So two kinds of approaches are available. So based on this observation, what we have understood so far, we suggest you can use white column with precautions, whatever I have explained in the previous slides. If you implement all those precautions, whatever I have explained, then you are very much okay with this. And it will give you much better control of your structural model compared to using shell element. Okay. But you can do shell element also, considering you are doing these two options. Then when you do using white column, what you have? It is similar to modeling of frame members, except the crack section definitions for shear wall. So you have to model using white column, but crack section definition should be corresponding to shear wall, not the one which is representing the columns or beams. Then you have the plastic hinge, which can be modeled similar to those of RC columns, either using moment rotation hinge or using fiber hinges. Then it is also going to be governed by the same backbone parameters what you have used for the beams or columns. And the plastic hinge can be assigned similar to those beams, but the location where it is expected in case of shear wall, usually at the base, but you can define in other locations also. So there is no harm. But the thing is, your computational time will increase, and those hinges will not be activated during analysis because it will not reach that stage of nonlinearity. So you can go with one or two hinges at the base location. That is enough. Then shell element we already discussed in the previous slides. Hinge behavior is governed by stress strain curve, so I can skip this one. Then in case of shell element, what you have to take care of other than, yeah, this is related to meshing, so you can talk about this. So meshing should be fine enough to model the adequate flexibility. If you do not mesh, it will be rigid, fully rigid. So again, it is not appropriate. So some iteration work you have to do to find out the number of mesh elements you have to use. Okay. So based on our uh, validation process, we have done a lot of trial works for that on iteration. So after doing number of iterations, we found if you use this 5 by 5 element, then that is enough, sufficient. I'll show also the comparison with the single element and with the frame element. What is the difference in result you get? Then beam connected to opposite ends of shear wall should be connected together using rigid link. This I already told you have to model the horizontal rigid link. And one more thing is you have to define the dummy beam with negligible weight and stiffness. This is required to transfer the load from this one frame element to shear wall. Okay, otherwise this load will not be distributed in the shear wall from the other portion of the structure. So you have to define this. But remember, this should be with negligible weight and stiffness because this is just a imaginary beam. It is not actually existing in the structure. So if you ignore the weight and stiffness, so it is very much like imaginary. Now see, whatever I talked regarding the meshing and these two, one is shell element and frame element. So this validation work we have done using a single shear wall and a coupled shear wall. Okay, so these results I'll show you now. And here you see we have used 5 by 5 meshing. Here also I have used, but I have not shown that meshing I have not shown. But one thing you can see is this horizontal link, two zigzag line is showing, and one dummy beam is also there, which is not visible here. Okay, then these are the comparison of result. Here you can see this is validation using the single shear wall in the first case, this one. So these are the stiffness modifiers we have used, I22 and I33. Just as an example, I took 50.5. Okay. Then I also took, these are two example. Okay. So this was the result I got using white column, and next using shell element with different mesh definition. First I have used without any meshing. By default it is single element one by one, and same parameters. These are representing the similar thing what is defined here. If you go by the comparison earlier what I have shown, so this will be similar. Okay, then you see this is the result I got. Then I have increased to 5 by 5 and see exactly whatever I got in the white column, same thing I got here. Then I have increased to see what further effect it has. So there is little bit variation but not negligible. Now if you want to increase number of meshing beyond that, see there are some variation but not that much significant. So you can go by this meshing but not necessary. 5 by 5 is enough. So that's why based on this experimentation, we suggest you can use 5 by 5 meshing in case of shell element. And this was done using the single element experiment. Similarly, I'll show the couple shear wall experiment. Again, same parameters. These stiffness modifiers are same. Only this is couple shear wall compared to the single shear wall earlier. So here also you see 5 by 5 meshing we have used, and the result is very much similar. So based on this comparison, I would suggest you take care of these things and use 5 by 5 meshing at least. You can go beyond that, no harm in that, but minimum 5 by 5 you have to use. Okay. Then rigid link, how you have to model. This I'll show in the software, but these are the degrees of freedom what you have to take care of. Okay. And this is I think about the local axis of this rigid link, which is coming to be the torsional mode in the structure. So this I release. Okay, other than this are fixed. So you can again do play with this one, release one and check what is the behavior, and like this we have also done the same things. And after releasing this one, the it was representing the frame element model. Okay, and this is also logical, you are ignoring the torsional one. Okay. Then see, we have analyzed the building one using the shell element shear wall, and this is the uh, you can say different modal behaviors. So in the first fundamental mode, first one is obviously fundamental mode. You can see the participation is 0.7061, which means 70%. Then in the second mode, again it is fundamental. Again we have 71.47%, and third mode is torsional. Okay, and it goes on like that. You have translation, translation, rotation, then translation, translation, rotation, then again it goes on like that. And this one is using frame element, means shear wall is modeled using frame element with the concept whatever I have explained so far. Okay, now if you compare this one, first mode was 70 point something in the shell element model, 70.61. In this case it is 70.36. So it is very much, means you can say almost same, both the models are almost same. Then you also have second mode at 71.22 here, and you have 71.47 here. So you can compare, our model is almost same in both the cases. So this was the part of validation for white column model. And I can suggest you to use this one since this is reliable, and it will reduce your computational effort in creating your model by a big margin compared to shell element when you are particularly going for performance based design. Because to run this analysis for a complex structure like you said 20 story and 50 meter by 50 meter or 20 meter by 30 meter plan area, it will be very much difficult to run this model. So if you want to use this frame element, your computational effort will be reduced by a significant margin. Next is comparison of bending moment profile for these two cases. This first case is for shell element shear wall, and this one is frame element shear wall. Okay, and you can see. And one more thing is your member should be decided based on the bending moment profile, whether it is a shear wall or column, not by some other definition. Okay, so by looking at the bending moment only, you can understand whether it is a shear wall or column. Okay, now you see in this case, it is representing a purely cantilever shape, which is expected in case of a shear wall. And this I got using the shell element, and similar thing you can see in case of frame element. Okay, so this also confirms the reliability of the frame element model. So this was a part of long experimentation work what we have done to bring this concept to all of you so that you can use this concept in your modeling and make the structural model as accurate as possible. Okay, and I expect if you use this one, your model will not be wrong, and it will also help in your computational time. And the nonlinear modeling part will become easy once you do with this model, because people always get scared about running the huge structure using shell element for nonlinear analysis. So once you do this one, that wariness will go away. It will not be there. Okay, so finally, this is the model what we are going to use from the next session for whatever I have explained so far to implement all these things in this example model. And it is a 12-story model with these plan dimensions and specifications. Okay, so don't worry if you have not understood some of the things so far. We'll implement in this model, and we'll see each and every aspect of modeling and nonlinear static analysis, which is pushover and time history analysis. Everything will be doing using this model. Okay, so this is what I had for today's discussion. Now I think I have to show one thing, how to define this rigid link. Let me show this first. Just I'll take 5 more minutes. Okay, I can open any model, no problem. So this is the model what we'll be using from next session. You can see here, and the definition of your springs, it will be here. Not spring actually, link, rigid link. You go to this, either you add or modify this one which is available by default. You just check all these boxes. Okay, so only this one you have to ignore. And this you can play with this how suppose you first try with one fixing and other releasing. Okay, and compare the behavior of model in both the cases, frame element case and shell element case. Then you fix one more and check. So you'll understand when you play with all these things, you understand how each of these are going to behave. Okay, so I think this is all I wanted to share. And now we can go to the question answer. Okay, thank you everyone. Actually, I have taken half an hour extra, so your question answer session is bit reduced. But no worry, whatever questions you have, we'll try to cover all those things. Okay. And
सर मेरा एक डाउट है
yes,
सेक्शन डिजाइनर में जब हम रेनफोर्समेंट प्रोवाइड करते हैं कंप्रेशन और टेंशन में तो दोनों साइड के लिए मोमेंट कम कर्वेचर जो है वो डिफरेंट आता है बट जब हम यूजर डिफाइन के थ्रू हिंज मॉडल करते हैं तो
हाँ,
उस साइड सर मोमेंट और कर्वेचर का जो आता है ऑप्शन उसमें हम कंप्रेशन का देते हैं या टेंशन का देते हैं
moment curvature do not see if you take a section, you are considering compression as well as tension. Let me go to this section once again. See this section, suppose you have now, I have symmetric. I have
सर
the
स्क्रीन
reinforcement.
विजिबल नहीं है
Oh, sorry, I have not shared. 1 minute. 1 minute. Actually, I think Yogendra Singh sir is not there. He also wanted to be present here during question answer. I'll just inform him and come back in 2 minutes. Okay.
Okay, sir.
Hello, am I audible?
Yes, yes, sir.
Okay, so he is busy it seems, so we can continue our discussion. I'll share my screen. 1 minute.
Yes, sir.
So you can see my screen now?
Yes, yes, sir.
Okay, so I was talking about this section. When you take the section, and in this case particularly, we have similar reinforcement arrangement in both top and bottom. Okay.
सर बट अगर रेनफोर्समेंट सिमिलर नहीं है कंप्रेशन साइड डिफरेंट है और टेंशन साइड डिफरेंट है तो मोमेंट कर्वेचर बोथ साइड डिफरेंट आता है
Yeah,
एंगल
yeah,
चेंज करने पे
it will be, it will be. Now let me explain. Now in this case, I have considered compression at top. Okay.
Okay.
So the whole analysis is going to be based on this assumption, compression at top. In your case, suppose you want to consider compression at bottom, so your analysis is going to be with that assumption. According to that one, you run your analysis, and if the section is symmetric with the reinforcement arrangement, it doesn't matter whether top or bottom or compression. In both the cases, you'll get same. But if your arrangement of reinforcements are different, it will vary. But concept is going to be similar. Okay.
बट सर प्रॉब्लम ये है कि जब हम फ्रेम के अंदर डिफाइन सेक्शन के अंदर जब हिंज के लिए डिफाइन करते हैं मोमेंट 3 अगर बीम की बात करें तो उसमें अगर हम मोमेंट कर्वेचर ऑप्शन को चूज करते हैं और वहां पे हमें मोमेंट और कर्वेचर की जब वैल्यू देनी होती है तो वो वैल्यू जो है वो अगर दोनों कंप्रेशन और टेंशन में रेनफोर्समेंट डिफरेंट है तो कौन सा मींस मोमेंट रोटेशन की वैल्यू वहां पे पुट होनी चाहिए
That based on, if you are doing manually the analysis, it is based on your analysis. But in software, if you talk about etab, it defines based on ASCII code. So whatever is given in the code, it defines accordingly. If you see, if you
सर
look at, hello,
आप एक बार सिर्फ ई टैब ओपन करेंगे मैं जस्ट आपको एक जस्ट व्यू दिखाना चाहता हूँ
okay,
Okay.
जैसे सर आप डिफाइन में जाइए एक बार सर, और फ्रेम वॉल नॉन लीनियर हिंज,
frame.
वॉल नॉन लीनियर हिंज जो सर
Okay,
बैक।
okay. It will be here assign frame.
No sir, we in the define section only.
Okay, non-linear hinge. Okay, sorry.
Yes sir.
Yeah.
Add new
So
property,
add new properties, concrete.
concrete,
Okay,
okay.
then
M3
maybe
कुछ M3, it's okay sir.
fiber PM3, some hinge
सर आई
you
एम
have to
नॉट
define.
सर, मैं फाइबर मॉडलिंग की बात नहीं कर रहा हूँ, ओनली
Okay.
लंप प्लास्टिसिटी की बात कर
Okay,
रहा हूँ।
okay, okay. I understood. 1 minute. Add new property concrete, and you want to talk about interaction hinge.
नो सर, मोमेंट 3 ओनली।
Okay, that will be for beam, right?
या
Okay. Yeah, tell please.
एंड सर अब यहाँ पे अगर मैं मोमेंट कर्वेचर ऑप्शन चूज कर लेता हूँ,
हाँ.
और यहाँ पे जब हम इल्ड मोमेंट की बात करते हैं तो स्केल फैक्टर जो है सर, ये अगर हम मोमेंट कर्वेचर पे अगर सर रोटेशन से कर्वेचर को ऑन करते हैं, तो यहाँ जो सर ये मोमेंट आप एक बार सर कर्वेचर पे ऑन करेंगे।
Curvature. Okay.
अब सर ये मोमेंट और कर्वेचर की जो ये वैल्यू है, ये कंप्रेशन साइड का है आएगा यहाँ पे अगर हम टिक करते हैं तो, या फिर ये बॉटम साइड टेंशन का आएगा यहाँ पे।
See here, actually it is showing only for positive axis now. Okay.
तो
But
सर
now
बट जब हम
listen,
सर
please
बट आप
listen, please listen.
ओके ओके
The hinge you define after running the analysis and complete your design, right? So once you
सर
complete your design, you have some reinforcement already defined there based on your design. After that, when you define your hinges, these parameters will be visible here. Some movement will be here in positive and some movement will be here, and some curvature also will be here. Okay, depending on how much capacity of curvature actually your section has. Now it is not there because we did not define any particular section to this hinge. Okay, so once you define that to a particular section, definitely these values will be there.
ओके सर।
Tajul,
Yes.
Pulkit, this side I would like to add, Rohit, you are checking the symmetric option, just below the this moment curvature one, there is a
Yeah,
symmetric
this
option.
one.
Uncheck
This
it.
so
In
you
the
can
top you provide the compression, in the bottom you provide the when the case is reversed.
Yeah. Sorry, I actually missed this point. So you can control here also. So you can uncheck this one and you can define here. Okay. So now based on your section, whatever section you got from the design, these values will be there.
ओके सर।
Okay.
Sir, excuse me,
So
sir. Excuse me, sir. Sir, excuse me.
yes.
Sir, can you go to the again, sir, to that part?
Okay. Yeah, please.
सर ये मोमेंट कर्वेचर जो टिक करते हैं, तो
हाँ.
इसकी वैल्यू हमें यहाँ इनपुट करनी है मोमेंट और रोटेशन के टर्म्स में। तो
हाँ.
ये वैल्यू हम क्या जो सेक्शन डिजाइनर में कर रहे हैं वहां से इनपुट करेंगे या बाय डिफॉल्ट वो वहीं से पिक कर लेगा?
You have both the options. You can define manually by your section design, and if you want to design based on some code specification like ASC, you can do both the way. You can do, no problem.
ओके ओके, ठीक है सर।
Okay, but one point I would like to mention here, when you are defining manually, I have just explained you the procedure. This is just a procedure you have to follow, but it is your responsibility to validate this whether whatever you are defining is correct or not. You cannot simply go by a particular method. You have done this method or whatever you have got, this you are simply inputting. It's not like that, because this is the actual structure and you have to verify whatever input you giving is correct or wrong. Okay, so always keep that in mind. So that's why if you do not understand completely these cases, then it is better to go by the established code specifications.
But sir, for few cases the codes are not there now. Like that key, if we are putting the stress sustain curve manually for the other than concrete, then we cannot follow the code.
Yeah, so in that case, first thing you have to do is try to find out some research paper, because there is means some research paper will be available in every aspect. Maybe in some field it will be less, some field it will be more. So your first duty, in case there is no code specification, First duty is to find out some research paper from well-established journal, then find out some experimental results and try to validate with the model you have created in your software. If it is working, suppose you can validate those results, what is given in the research paper, then you can definitely use that.
Sir, one more question I have.
Yes,
If
please.
I am going with this, अगर मैं कोड यूज कर रहा हूँ AC
हाँ
4117 यहाँ
हाँ
पर मोमेंट रोटेशन या मोमेंट थीटा के लिए बाय डिफॉल्ट वैल्यू,
हाँ
और सेम चीज को अगर मैं फाइबर इंच से मॉडल कर रहा हूँ तो दोनों का रिजल्ट इस ई टैब में मैच करेगा या डिफरेंट आएगा?
No, it will not match. But suppose you are defining using moment rotation, it is not assuming the interaction in both the axis, x-axis and y-axis. It is considering the action only in one direction. But if you consider the fiber action, it will also consider the interaction. So there will be some variation of results, but it is not drastic that one option is unreliable, another one is reliable. It is not like that. But result will be, there are some variations, still it will be close.
Okay sir, got the point. Thank you sir.
Okay.
सर स्लाइड नंबर 3 में जो आपने एक्सपेक्टेड स्ट्रेंथ का बताया है, सर एक मिनट प्लीज स्लाइड नंबर 3 में आ जाइएगा।
या प्लीज।
सर ये जो एक्सपेक्टेड यील्ड स्ट्रेंथ है वो Fy प्लस 1.64 इंटू सिग्मा एस लेना है या फिर कंक्रीट के लिए जो आपने फर्स्ट फॉर्मूला बताया है सर वो लेना है?
In case of steel you are talking, right?
नो सर, कंक्रीट।
In case of concrete, this one, whatever I have shown here, 0.8 into 0.85 into FCK plus 1.64 into sigma, this should be taken for expected strength. If
सर
yours
बट कोड में कहीं पे लिखा है स्टील के लिए 1.25 इंटू Fy, तो सर वो
no,
एक्सपेक्टेड
that is different thing. 1.25 into Fy, that is just conversion factor for ultimate strength to yield strength. That is not expected strength.
ओके, सो मींस सर कंक्रीट के लिए एक्सपेक्टेड यील्ड स्ट्रेंथ में आप फर्स्ट फॉर्मूला बता रहे हैं और स्टील के लिए आप सेकंड बता रहे हैं। ओके, थैंक यू सर।
Yes.
सर अगेन लास्ट क्वेश्चन इज, सर आपने शेयर वॉल मॉडलिंग में 3 डिफरेंट मॉडलिंग बताया है, उस तीनों डिफरेंट मॉडलिंग में जो हिंज का डेफिनेशन है वो सेम ही प्रोसेस रहेगा या चेंज होगा? क्योंकि हिंज का जो लोकेशन है वो कहीं उसमें वेरिएशन आएंगे क्या हिंज
Hinge
डिफाइन में?
location will be same whether you're modeling using shell element or modeling using frame element. Location will be same. Okay. Only difference is going to be here. Sorry, not here.
Sir, what is the value of sigma?
Difference is going to be here. This is using frame element. Okay, so normally when you define your stiffness modifiers for column, the parameters you do not define like that, right? You define only these two parameters. For column I am talking, but when you are modeling for shear wall you have to define parameter like that. So this is the difference. And another difference is the hinge should be located wherever it is expected in real shear wall. Okay.
ओके सर, थैंक यू सर।
Yeah.
गॉट इट।
Hello.
Sir, I have one question.
Yes, please.
Can you please go to slide number 3?
Slide number 3. Yes.
Yeah. Sir, this is FCK plus 1.64 standard
See.
deviation is
Yes.
actually the target mean strength
Yes.
when we design the concrete.
Yes.
And then normally we don't use that while designing, and it should not be with the 1.64 when we come back here for FC expected.
This is not for design. See, these parameters, I think there is some misunderstanding. See, again I am telling, this definition should not be used for designing any structure. Okay, this should be used only in case of performance based design when you want to estimate the capacity of your structure. Okay, see,
But then that capacity is already taking into consideration the target mean strength, which ensures us the FCK.
see this, if you look at this probability distribution, here is our FCK. Okay, this is not mean. This is not mean, right? Mean is this one. Now the meaning of mean is this is the most probable value, means I expect in most of the cases strength to be this one, not this.
Yeah, because it was target mean strength while designing.
No, in design you didn't use this. In design you have used this one always.
No, concrete makes design.
Okay, in concrete mix design.
Concrete mix design base has a base of FCK plus 1.65
Yes,
times
yes, yes, yes,
standard deviation. So
yes.
are we depending on the target mean strength, which is not used next, and it is just insurance that we will get the FCK all time?
No, see,
That is
I'll
expressed in
explain.
time.
I'll explain once again.
Yeah,
This FC is, suppose you have 100 concrete cubes.
yeah.
You have prepared these concrete cubes using FCK value of 20, means M20 concrete I'm talking about. So you have used the specification given for M20 concrete, and you have prepared 100 samples of concrete cube of 150 mm site. Okay, now you have done laboratory testing for compression strength of those 100 cubes. So based on those experiments, if you plot this curve, this median value will be come out to be same as this one. It may not be exactly same, but it will be close to that. So this is the
Yeah.
background actually.
Okay.
सर सिग्मा एस की रेंज क्या है? मतलब किस चीज पे ग्रेड पे डिपेंड कर रहा है? तो सर इसकी
Sigma
सिग्मा
is,
सी तो ऑलरेडी आई.
see, sigma is it is depending on different parameters. Some parameters are known to us, some parameters are not known, because if you talk about concrete, it is a mixture of aggregates. It is a aggregate, then cement, then sand, then water. Okay, so once you mix all those things, all are having different properties, and you mix together, again it is creating a new different property which we do not fully understand. Okay, so this meaning of sigma is the deviation, means variation, which is not taken into account in estimation of this. Okay, so to take the safety into account, we consider this one sigma. This variation is coming from this probability distribution work. Okay, when you prepare the distribution based on large number of experiment, you will not get a single line. It will be a range of values. For example, from here to here, number of range will be there. So if you take average of those range, that average line is represented here, and from this average line, the extreme point of that range is represented by this sigma.
सर स्टील में एफ 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 500 के लिए सिग्मा एस की वैल्यू क्या होगी वैसे?
For steel, actually sigma is close to 30 to 50, I said. You can use 30 mostly. Okay, but it may be between 30 to 50. In my whatever research I am doing, I have done lot of calibration, and I found 30 is okay. If you use 30 for steel, irrespective of grade, except F2 250, that is mild steel. So I am talking about HYSD, either it is 415, 500 or 550. So you can use 30.
सर इसका कोई रेफरेंस मिलेगा?
Reference you can get only based on experiments. You try to find out some experimental results, like research papers which have done the tensile testing of steel of lot of means lot of specimens, and there you may get.
Okay sir, thank you sir.
Okay.
Hi Tajar, you have considered property
Hello, sir.
modified
Mohammed
this
Salah
year?
from this side.
Hello.
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 Sir, Mohammed Salah from this side.
Yes, please.
Sir, I have one question regarding shear rigidity.
Shear rigidity,
The
yeah.
shear modifier for shear
Yes,
wall.
let me go to this 1 minute. Yeah, please.
As per 1893, you have shown one slide based on 1893 part 1.
Yeah, this one based on can you see my slide?
No.
I think it's loading. Just wait for a few seconds.
Okay.
I think we should not consider property modifier for shear, right?
You can consider.
Should we consider shear modifier?
You can.
in
You
shear
should. You
wall?
should. That's why it's given in code, right?
No, nowhere code mentioned, right? For property modifier shear, only for flexure. Moment of inertia, we have to reduce.
See, normally our behavior is governed by flexure. If you model the structure frame member, so it will be governed by flexures. We do not expect shear to occur anywhere. That's why we can ignore, no problem. But suppose at some particular location you are expecting member to be failed in shear, that time you can consider.
My
First thing is
question was
in code
here.
one
One thing.
1893 shear property modifier shear is not there.
Okay.
Second thing is generally concrete will crack during tension. That is coming from the flexure only.
16700.
Yes. That is the basis actually.
So yeah, but why property modifier shear is considered? That too in frame you have considered, and for not considered for shear wall you have considered.
In my
In
example,
frame.
are you talking about in my
Yeah.
example? No, I didn't
In
use
your
shear
example.
modifier. I didn't use my shear modifier.
Okay, can you go? You have applied for area.
Apply for area. Can you tell which slide you are talking about?
Property modifier for shear wall.
Property modifier for shear wall. Okay. 1 minute.
No, I think can you go to second one?
Second, this is
Next slide.
okay. Yeah, this one, right?
In this cross section area, you have considered 0.35.
Yeah, the cross section area because of this definition. I think I have to show this once again. 1 minute. See, this cross section area because of axial load, because of flexure, and because of movement also. Okay, so that's why you have to define this cross section. Okay, this is not for shear.
And if it that is it is okay for F2T if it is F2T is varying, but for the direct axial force it is wrong, right?
No, axial force. Yeah, axial force.
If the F2T is varying on the length of the shear wall, it is fine. For the direct axial force, uniform axial force F2T, it is wrong.
So, do you expect any failure in the concrete because of axial force?
Yeah, there can be because there's sometimes very high axial force in columns for
Yeah,
shear walls.
in extreme cases you can, but we do not expect
Usually
generally failure
columns are
under-
compression members, even
Yeah.
once also.
So yeah, generally failure occurs because of flexure. So compression, I don't think it will be causing any problem.
But in gravity, compression is the main concern, no? But we have same model
Tajul.
for gravity and earthquake also.
Hello.
Tajul, may I add something?
Yes, please.
So Suresh, if you go to the moment curvature curve and calculate the EI that you are getting.
Yeah.
So if you find that the EI that you have assumed for your beam and the EI you are getting with respect to the moment curvature curve, the both are different. If we go to the curve of moment curvature that we are plotting, yeah, any moment curvature curve.
Yeah, this one.
If we go by this and we check the linear portion curve, the linear range in which the curve is going, and if we calculate that, we know that m by I is equal to E by R, which is equal to m by phi is equal to EI.
Yes.
Yeah, I know that curve will deviate at the MCR value.
Yeah.
That is
So that linear portion, if we calculate the EI, it will be approximately the codal recommended values that effective EI you are taking it.
Yes.
However, when you move towards the axial failure, shear failure, you haven't changed your section stiffness anyhow. So it is recommended that you use those stiffness like reduction in the shear, reduction in the axial strength for the sense of conservatism. That if my moment curvature which I am giving, which is taking a flexural rigidity, I have reduced by a certain margin. So I reduce all other rigidity as well by a certain margin.
Yes. So you are already in the safer side, right? No need to be worried.
Yes.
Maybe sometimes too conservative.
See,
so
when
much
you talk
will
about
be
this
fine.
conservatism, see, it will come only when that picture is all means occurring in real. Normally, you do not expect failure. If you take 35% of cross-sectional stiffness also, you do not expect failure in most of the cases because of the pure compression loading. Because our gravity design is very much overestimated already in terms of capacity because of lot of load factor, partial safety factor and all. So that failure will not come really.
Sir, I have one doubt, sir.
Yes.
Sir, you discussed about layered shell technique where we need not give the hinge properties.
Yes.
It will automatically do non-linear analysis through which
Yes.
it will find where the failure will occur or the where the hinge will occur. It will automatically account that. So do we have this thing in wide beam, wide column also?
No.
Like layered?
In wide beam, you have to define hinge manually, like what you do in case of column.
Okay, so in this, like if I have a good system, like very good workstation, if I do layered shell technique, if I use layered shell technique, and I do carry out analysis, so the hinges I will get from that, will that be sufficient, or we are giving hinge from our side, we are deciding the location, so all these things will be skipped in that or not?
No, actually in layered shell, the concept of hinge itself is not there, because that whole section is acting as a nonlinear region from bottom to top. Okay, so nonlinearity will be occurring in the entire length of your member. But the thing is, at the point, suppose if you talk about base, the nonlinear behavior will be higher compared to the other region. Maybe the curvature or rotation what has occurred is very much higher compared to the other region. So that is the difference, but it will be fully nonlinear from bottom to top. Okay, there is no concept of hinge if you model using layered shell element. And this nonlinear behavior will be taken care by the stress strain curve of your material. Okay.
So sir, what the difference we will get, like from hinge analysis we do what we get, and from this analysis what difference we get? Like we are getting the
Difference
collapse condition, or what we are getting?
difference is 1 minute. See, I talked about the crack section properties, right? Now, if you model your shell element using layered shell, you do not have to either layered shell or elastic shell with the plastic hinge. Okay. In that case, you do not have to define this uh, cracked section properties. Sorry, in case of shell element, you have to define, but layered shell, I didn't use actually. I have to look at it, how it behaves. You have to define crack section properties here also. The difference, I have to do experimentation again because the validation process should be done before making any comment. Okay. So,
Sir, can you explain rigid link for shear wall and beam once
okay.
again?
Okay. Okay, actually rigid link, why we do is, let me open one example.
And also gives the idea about how to assign the rigid link.
Yeah, these things will be
Basically,
given. Don't worry. When you start with the model, what I have shown at the end, one building plan I have given, this will be analyzing throughout the sessions, right? So all these things, whatever I have explained today will be implemented. Don't worry.
okay.
So let me show the analysis result. Okay. Let us take one lateral load case. Okay. Now you see this rigid link is connected between this and this node, not connected with any other intermediate node which is created by meshing. Okay, I have connected only these 2 points by this rigid link, and this beam is connected to this rigid link, means directly you connected this point, so it automatically gets connected to this link. Okay, similarly here also. Now what happens when you run analysis and show your means see your behavior, structural behavior, this deformation pattern is very much expected, right, as per our general
Yes, sir.
understanding. But
Yes, sir.
same thing you can see without using rigid link. In that case, what will happen, this beam, now you can see this beam is actually in double curvature.
Yes,
But
sir.
if you do not use this rigid link, it will be like a straight line. Means in that case, this point will be acting as a pin connection instead of a rigid connection. Okay. So that thing is taken care by this rigid link, and it also depends on your meshed definition. As your mesh becomes finer, this will try to act like a pin connection. Okay. So that's why we mesh it properly and use this rigid link to take care of this thing.
If any beam coming from a perpendicular direction.
It doesn't matter. In perpendicular direction, behavior will be same in all the cases.
Okay. Only in plane beam.
Yes.
Okay. Thank you.
Okay. So can
So,
we?
Okay, sir. Can you give reference for
curvature
the
for
190 for
columns.
One by one,
rigidity?
please. One by one, please.
Yeah. Moment curvature for
Sir,
column.
can you please
Can
give
you
the share
explain that?
reference for
We'll
1893?
come to everyone,
Or
please. I think Mohammed Tala Siddiqui, you can proceed with your question.
Can you give the reference for in 1893 for shear rigidity that you have shown in your slide?
Yeah, you can use. Why not?
But in code we didn't find this
One
modifier.
second,
Can you give reference
can I
for
answer
page
this,
number reference or
Tajul?
article number
Yeah,
reference?
please. Someone is trying. I don't know.
Tajul, I'll answer. I'll answer this.
Yeah, please.
See, this is nothing but basically when you're doing it, when you're taking the shear rigidity, that's only basically the conversion of E and G. G is like 0.4. So it's only that. So since you are defining it by E, so that's why you can do it by 0.4. But really speaking, in a non-linear in a linear analysis, doesn't make much of a difference. We have been doing it for long. It doesn't make much of a difference in a linear analysis.
Yeah,
So
actually,
not to worry about it. Don't worry about it.
I think that point. Yeah, I missed. Let me explain this once again so that everyone
Equals
get
to
clarification.
4.4 of G. That's how it is done.
Yeah.
Okay?
So I think that confusion has created because of this. See, this is in terms of E, okay? But your shear stiffness is not in terms of E. It is in terms of G.
Exactly.
Okay. So 0.4 into E is becoming E divided by 1.1 plus mu into 2, right?
Yes.
So from that definition, you are getting this one. So in terms of G, if you talk about it is full rigidity. We have not reduced actually.
Okay.
Actually, that multiplier is for I, right? Not E, no. Why are converting E to G? It should convert from I.
See, shear is defined in terms
E
of
to G.
area. Shear is defined in terms of area. So you have to, shear rigidity is GA, not EI. EI is the rigidity for
I know
flexibility.
we know GA, but 0.35 to 0.35 E2 we are selling 0.4 G something, right? But it should be it is I, 0.35 I, not 0.35 E. Although it is common EI, because cracking, not about the material nonlinearity. We are telling about
It's fine. Is it making any difference if you're at 0.35 I or 0.35 EI? E is constant, right?
since you are telling about conversion from E to G.
No,
that is only
okay.
only for the shear, because shear rigidity is not EA, it is GA. So just to convert it into in terms of E, G is being replaced by 0.4. I think this. Don't worry about this point. It's not going to change much.
Yeah.
For a linear analysis.
So we are talking only about this last column, not this one, flexural stiffness.
Okay.
Hello?
Yes.
Sir, I have one question.
Yes, please.
Do we need to define and assign unconfined and confined concrete separately in, for example, in shear wall?
In case of performance-based design, you have to do. If you do by ETAPS or SEP, because if you take the default section, what is available in the frame definition, so I do not have this. I think considers. I forgot whether it considers or not. If it is not considering, then you have to define it manually. If it is considering, then you don't have to.
Okay, for example, we need to assign the separate material property to the boundary elements and the mid zone, correct?
Hello? Hello? Am I audible?
Yeah, you are audible.
Yeah, please.
section
case
analysis of
share
column. Uh, that was the one question
Yeah,
I wanted to ask.
Bhushan, yeah, I think you're trying to say something, Bhushan.
Yeah, section analysis for column, like we are doing it for beam.
Hmm.
Okay, so beam is easier, but when we go to the column, we are doing it layer wise, the stress strain analysis for
Okay.
the columns.
Okay.
Whatever are coming in the one layer, the
Mhm.
reinforcement per layer we take into that number of layers
Mhm.
for column. So for manual, what is the procedure like this we can follow for beams?
Same
But
procedure.
what can be,
Can you see my slide?
yeah,
Okay, so suppose this is column. Let's say this is column, and this axial force is acting in the column, and I have layer of reinforcement. So I'll just copy some reinforcement. Suppose I have reinforcement here. I have reinforcement here. This is the question you asked, right?
yes, yes.
Okay, so let me put some more reinforcements. And also at the top. So now what you have to do, the number of layers you have, number of force will come, right? Here you have force for this reinforcement. Here you have force for this reinforcement. So procedure is going to be same, just your calculation effort will increase. You have two additional forces. So this C is equal to T now will become, this C is actually the means components of this C can be only C or C plus this steel or this plus this also, depending on where your neutral axis is actually located. Let's say now your neutral axis is here. So this whole thing, this is going to be your C, right? Then only these two are going to be T. So there is no change in the procedure. Only the additional forces because of additional steels should be considered. Is it clear?
Yes.
Okay. So do you have any more
So
questions?
internal forces we are just analyzing. Let us say the neutral axis outside the column, then full section will be under compression. So C will not be equal to T. C will be some value in that particular case. Most of the time we get the neutral axis outside the column when we are analyzing it, or at the face of the column. So in that case, full section will be in compression.
But you will get still moment
So
capacity, right?
yeah, so moment capacity will be there, and the compression side, whatever the strain is there, we can take on that ECT. That would be available to us.
So let's say your neutral axis is here, and instead of this, now I have, okay, it is going in other direction. Let's say something like this. Okay. So now your neutral axis is here, your whole section is in compression. So when determining your forces, only this much of your stress strain curve should be considered instead of taking full. So this is the difference. And when you are determining your moment capacity, you have to always determine with respect to the central axis. Suppose this is the
So my
center.
assumption, initial assumption that where my neutral axis will be, I need to first find that, then I can do this particular thing.
Yes, so it
So
is iterative
while
process.
coding, it will become basically some issue with respect to that, because first I have to analyze whether the neutral axis is inside or outside, or at what position it is, which
Yes,
is
yes. I
governed by
think
the
I got your
reinforcement.
point. Let me show my code and I'll try to show what I have done. Actually, I'll also share this code. You can use this and try to understand what I have done. But I'll show you that portion what I did. Okay, so one more thing I forgot actually before answering your question, just let me show you one. Actually, you can use Python for doing this nice stuff of things. Just let me show. Not only Python, you can do anything. You can use any coding platform, whatever language you are expert with, and you can prepare these things. This actually that moment curvature by Python code, whatever I have shown, I try to prepare means make a GUI for that. Okay, it is still in process, but still it works. Half of the, not half, almost 90% is implemented. So last step is pending that I didn't get the time to implement. So whatever I have shown in the code, that same thing you can do here. So this is still not completed. Once it is completed, I'll show share this also. Okay, so your shape of cross section you define here, and the background. This will also give you the idea when you use any software what is going on in the background. Okay, we do not usually understand. We just use the buttons what is available in the front side, and background. Some calculations are going on. We do not know. Now you see you just use rectangle, so your factor shape factor as I discussed for rectangle it is I think I just used the wrong value for this one. It should be 0.75 for or vice versa. I have to check it, but values what I have defined it is coming. Then you use for circular it is coming 1. So this is based on the definition what I have given. Maybe I have to check this once again. Okay, leave that part. Then concrete test specimen type, when I choose cube, so the factor as I told it is 80%. Okay, it is coming here. Then you choose cylinder, it is coming 1. Okay, then you define your member, for example 400, then height 400, nominal grade let's say 30 MPa, grade of main bar. Here I am giving only nominal values because expected values will be calculated inside the code. Okay, then grade of shear let's say 415, clear cover let's say 40. So everything whatever I entered here it is going on here. Then dia of shear is 10, gamma of rebar, since we are doing expected properties it is 1, for concrete also it is 1, the spacing of shear rebar let's say 150, then number of legs in x2 in y2, then standard deviation is 5, then standard deviation for this one steel 30 as I told, permissible strain in concrete. So this also is calculated, but let's say for concrete maximum limit is 2. Actually I forgot to tell this one. In case of confined concrete, maximum limit of permissible strain in concrete is 0.02. It should not exceed this value. Okay, so in case of steel earthquake loading it is 0.05. Normally it is minimum 14.5%. Then axial load 1000 kilonewton. Number of rebar layers. So same as this example, number of rebar layers 4. Yes.
The input are not shown in the screen.
You can't see.
Okay, screen is not visible.
Window is frozen.
Okay, just wait for a few seconds. When it comes back, let me know. I'll show once again. It's evening time actually, so lot of people use the net at the same time. That's why it happens. Let me know when screen is coming back.
Yes.
Okay, so you can see this interface GUI. I am just
Yes, sir.
moving this. Can you see that? Hello.
Yes.
Okay, so if you can see, Now I have defined these parameters here, and in the background all the parameters are just taken into consideration by the code. Okay, then number of rebar layers, I am assuming 4 number of rebar layers, means this 4. Let me show. I have 1 layer, 2 layer, 3 layer, 4 layer. So 4 layer of rebars. And if you see the diameter of rebar in first layer can be different compared to the other layer. So I have to define for which layer what diameter.
Sir, screen is not visible, sir. Stuck, sir.
Okay, I'm extremely sorry for that. I do not have control on that. I have to wait just.
Hello. Manual
Yes.
understanding for this problem will help. Coding we can get hold slowly.
Yes,
So
yes,
if we can just close this
yes. Okay, so I
model
think
as
Bhushan
in
had this one, how to take into account this strain variation. Let me show that. Okay, so there are two different strain range. One is for steel, another one is for, sorry, one is for concrete from 0 to maximum strain in concrete, and one is from steel. Okay, so what I have done, I have created a loop. In outer loop, I have taken the range of strain in concrete. Then in the inner loop, I have taken range of strain in steel. So what you'll do, for each strain value in the concrete, it will calculate for all the strain values in steel. And wherever that C is equal to T is satisfying, that will be taken as output. Okay, suppose as an example, you have strain in steel as 0.0004, for example. So at this strain, you will consider all the strain in steel, and you will calculate C or T and try to satisfy that equilibrium condition. At whatever strain in steel that condition is satisfied, that will be considered as your output. Then once it is achieved, then you go to next range of your, sorry, next value of your strain in concrete. Okay, so this is the way I have done. You may have different plan, different thinking in your mind. You can implement whatever idea you have. So I had this idea, so I have implemented this. It's entirely depending on what idea is generated in your mind. Okay, that's all. So we can stop here, I think, and whatever question you have asked in the question and chat box, that we'll try to answer. Okay. Okay, fine. If not any more questions, then we can close this session. And thank you everyone for your participation. And we'll see you once again in the next session. Okay. Thank you.